Recursion is one of the most popular topics that gets asked around in technical interviews, and now we are going to do a full course on recursion. I can guarantee you that by the end of this course, you would become an absolute expert in all sorts of recursive problems, and you should be able to solve them very easily in your technical interviews. We will understand that what is recursion, how to identify it, where it gets utilized, what are the different alternatives, and all sorts of different lead code problems. So I'm going to put my utmost attention. I hope you also enjoy the video. So recursion is the art of solving the bigger problem by dividing it into bunch of different smaller problems until we reach to a problem that is so small that we know the answer, and then building the answer backwards. Presume that all of these stacks that I currently have on my table, they are currently presenting rows in a movie theater. And let's assume that we are currently sitting at this blue guy at this blue location. And we want to figure out that from this blue guy, how many rows are currently in front of us. We don't have any idea. So what is going to be the simplest way we can achieve this? The idea is quite straightforward. We are currently sitting at this blue location. So we are going to ask its predecessor or the person sitting before that, hey, what is your location? Since this guy also does not know, we are going to keep on asking the same question again and again to all the different guys who are currently sitting until we reach to the very first position. And this person says that I'm row 1. So because this person is row 1, it is going to convey this message that, hey, I'm this row 1 to this purple guy. And then it's just going to fill out that information. Same way, this is going to respond back to the original person who asked that what is your row position by saying that I am currently position row 2. So this person knows that I'm row 3, and this information would keep on getting propagated backwards and backwards until to the very first point where we originally started asking the question. And now here we are, and we can actually see that we have the answer sitting right over here. Now notice that there are currently these 7 kidney beans in this position. So we can say that we are actually position number 7 in this whole sequence. Now notice that what are the couple of things that we did. Number one, we just asked a simple question to from this guy to this bigger guy saying that what is your position, and then we kept on repeating the same question to a smaller and smaller subset. Eventually we reach to a case where we know the answer for sure, and this is our base case. And then once we found the answer for the base case, we started building the answer backwards, and we kept on doing that until we reached to a position where we wanted to get the answer, and we got it in the form of kidney beans. Now this demonstration might look simple to you, but what you did is absolutely use recursion to its finest, and you have utilized all the principles of recursion. Recursion is nothing but dividing a larger problem into bunch of different smaller problems until you come to a position where you know the base case, and then from the base case you call in the reverse order for the sequence until you reach to a point which originally requested the answer, and that is going to be the recursive call stack. Now this structure is going to look very similar to the Russian dolls that we are all used to seeing, and that is also a form of recursion. Recursion naturally occurs in a lot of different places in nature, and it's a very convenient way for us to solve problems. There is a beautiful example of Fibonacci series. That is also an example of recursion in itself. And then we can use recursion on dynamic programming. We can use recursion on our graphs, trees, arrays, linked list, all the different data structures that you can imagine. Because remember, in our scenario, this is the guy that is the last row setting that we did not find the answer for. But presume that we already started noticing all of these answers and all of these results. Now we know that this person was sitting just before this, and imagine if we had used dynamic programming to calculate all of these answers, and then someone asked me that what is going to be the row position of this yellow guy. I can clearly say that this person was sitting on the 7th position. Then this person also has to be the 8th position because we have already memoized or stored this information in our recursive array or a variable, and this is the true example of using dynamic programming with recursion to solve a problem. Now remember a couple of things. Any problem that you can solve with recursion can also be solved iteratively, but we just did it with a simple question, hey, what is your position, and then expecting an answer back. Now let's try to understand that how you can identify by looking at a problem that whether we can solve it using recursion or not. So there are some signs that you need to be actively asking yourself. And number one is that, can I solve the given problem by dividing it into a smaller and smaller set of subproblems? Remember what we did with our example. We took one problem and then we started uh, creating subproblems for much smaller group of inputs, and eventually we got the correct answer. Next thing is, we should be able to define a base case to stop recursion. We cannot go infinitely without having a base case. Then we would run into all sorts of issues with stack overflow and memory overflow and overall just a bad solution. So you should always have a base case for any of the smaller problems that you are creating. Once again, in our example, the base case was the white small container that was the very first row in our movie theater. But all in all, you need to have a base case. Next, if the problem is naturally hierarchical, data structures such as trees, nested structures, subsets, even graphs, then there is a very high likelihood that recursion should be able to solve the problem. And if you see any problem where you need to explore all the permutations and combinations and subsets, of course, recursion is going to be one of the solutions. I'm not saying that it is always going to be the solution. You can, any problem that you can do recursively can also be solved iteratively. So that's a given fact, but you can think of recursion in those scenarios. And lastly, whenever you see a problem that requires a lot of back and forth between any two endpoints or any two cells in a matrix or something like that, or you are doing a lot of backtracking, then there is a very high likelihood that you can use recursion to solve the problem. Now, many times, recursion can also lead to solutions that are brute force in nature. But if you're doing recursion with backtracking for a brute force solution, you can always store those results and then use it as a dynamic programming solution. So recursion is very powerful and can be used with a lot of different data structures, and that is exactly what we are going to see next. Okay, so data structures where recursion is commonly used. Number one, trees. We already talked about it. It has a natural order. It is a natural fit for recursive problems and solutions. And whenever you need to do a DFS travels or depth first search travel using pre-order, in-order, or post-order traversal, a recursion is a great way to accomplish that. Now, trees and graphs go hand in hand, so you can also utilize the same set of recursive principles for many different graph-based problems. So whenever you need to do a graph traversal, which is always going to be a case for any graph or tree problem, you can start to think about using recursion, because you would be doing a lot of backtracking with graph problems, especially if you're doing depth first search traversal. Now, same logic can be applied for arrays, where if you see problems such as finding subsets for given array, or binary search, or partitioning within an array, then a recursion is a great way to do it, because once again, all of these also rely on the same principle of dividing or coming to a smaller and smaller subset of an actual problem and building the solution that way. Now, linked list is very similar to graph and trees. It's like a linked data structure. It's not linear as array, or it's not stringent, but more or less you can use recursion for all sorts of different cases. And strings is just nothing but a different representation of an array. It's a character array that is defined with some specialized libraries. So overall, you can also use recursion for all sorts of string related problems. And matrix is actually a two-dimensional or multi-dimensional array. And funny thing is, matrix can also be one of the representations for the graphs as well, because we use adjacency matrix to represent a graph, and we need to traverse and do a lot of back and forth on all sorts of DFS based problems and solutions. So we would also be leveraging recursion quite heavily on 2D matrix related problems. So this is the main data structure that we are going to be leveraging recursion for. Now let's come to the meat of our whole entire course. Let's start diving deeper into the actual interview problems that we are going to be solving using recursion. And by doing so, we would understand quite substantially what recursion is, how to implement that, and along the way, we would be learning dynamic programming, graph, trees, and all sorts of different problems that are very heavily popular in technical interviews. So, let me know what do you think about these. Now, without any delay, let's get started. So let's try to understand the classic Fibonacci number problem. This is a LeetCode easy problem, and the problem statement is quite straightforward. We are given a mathematical equation that if we have to calculate the Fibonacci number of any particular given number n, it is going to be sum of Fibonacci of the previous two numbers. That's it. And then we are given couple of base cases where Fibonacci of 0 is 0 and Fibonacci of 1 is 1. So let's assume that if we have to find out the Fibonacci of 2, then the answer is going to be Fibonacci of 1 plus Fibonacci of 0, and we know that Fibonacci of 1 is going to be value 1 and Fibonacci of 0 is going to be value 0. So Fibonacci of 2 is also going to be value 1. Now let's try to calculate the value for Fibonacci of 4. So in this case, we need to calculate the sum of Fibonacci of 3 plus Fibonacci of 2. Now for Fibonacci of 3, once again we will have to calculate the sum of Fibonacci of 2 plus Fibonacci of 1. And for Fibonacci of 2, we will have to find the value of Fibonacci of 1 plus Fibonacci of 0. Now, once again, in this case, we already know the answer for Fibonacci of 1, that is 1. But we don't know the answer for Fibonacci of 2. So, we will also have to calculate that, and that is going to be Fibonacci of 1 plus Fibonacci of 0 and plus whatever this value is, that is 1. So in this case, now we have value for all of these three cases. So this value is going to be 1, this value is going to be 0, and this value is going to be 1. So 1 plus 0 plus 1, so this equates to 2. So we can say that both of this equates to 2. So we can notify that Fibonacci of 3 is going to be 2. Same way, Fibonacci of 2 we already know based on this equation that this is going to be 1. So this equates to value number 1. So overall Fibonacci of 4 is going to be combination sum of Fibonacci of 3, which is 2 plus 1. So Fibonacci of 4 is going to be value number 3. So this way we can calculate any particular number that we wants to find the Fibonacci number for. So now let's talk about the potential solutions for this problem. And remember, this is a classic lead code problem or a mathematical problem that can be very easily solved using recursion. So we will try to solve it using recursion, but I will give you a simple caveat later down the solution. So let's understand that by just looking at the whole this solution, we can notice that we are doing a lot of repetitive work. Number one, and number two, we are repeating the same problem for different input and we are going smaller and smaller and smaller. And that is exactly the scenario where we can use recursion to solve this problem. We can create a recursive function that its sole purpose is to get any particular number n, and then will try to return the results by doing the sum of Fibonacci of n minus 1 plus Fibonacci of n minus 2. And at any given point, let's assume that for recursion we need two items. So we need a recursive function. So we already created the recursive function that is already given as part of the definition. We also need a base case, and base case is also given, where if we want to find out the Fibonacci of 1, that is going to be value 1, and Fibonacci of 0, that is going to be value 0. So by applying this logic with recursion, we can solve this problem very easily. That if you want to find the answer for Fibonacci of 3, so in this case for our recursive function, we are saying that, let's say the name of our recursive function is fib, and we are trying to generate answer for fib of 3. Now in this calculation, first we are going to check that whether this value is either value 1 or 0. It's not, so we will have to do something else. So what we are going to do is we will try to calculate the answer for Fibonacci of 3 by calling this Fibonacci function again with all the values that we are trying to find answer. So we will try to call for Fibonacci of 2, and we will also try to call with Fibonacci of 1. Now for Fibonacci of 1 we already have the answer, so eventually we would get that answer in return. But for Fibonacci of 2, we don't have the answer. So we will once again recalculate and repeat the same problem, and we will call Fibonacci of 1 and Fibonacci of 0. and we will try to get answer that way. So recursively, try to understand it using a recursive stack, that what are we doing or what are we putting in. We need to find the answer for what is the answer for Fibonacci of 3 is going to be. We already know that for Fibonacci of 1 the answer is going to be 1, and for Fibonacci of 0 the answer is going to be 0. But for Fibonacci of 3, we need to find the answer for Fibonacci of 2 and Fibonacci of 1. So we put one entry over here, Fibonacci of 2. Now for Fibonacci of 2, we don't have an answer yet. So once again, we are going to repeat the same operation, and we are going to be calling Fibonacci of 1 and Fibonacci of 0. And in this case, because we have both of these answer as 1 and 0, so we, based on these two combination, we would get our answer back for this Fibonacci of 2 in a recursive call stack, and that value is going to be 1. And after getting that, now for Fibonacci of 3, all the values we need, we already have that answer. So now we are going to recursively do a backtrack to the original person who initially called us and return back the answer, and this is the sequence of event that is going to work. So now we understood the concept of recursion using Fibonacci problem. Now let's try to work upon the optimal solution as well. So first of all, what is going to be the simplest brute force approach? It's the exact same recursive call stack that I just explained. We can keep on using that, where for any particular number that we wants to get answered or answer for, we can keep on calling different Fibonacci numbers, so on and so forth. And we will eventually get to a base case that is going to be the answer that we are looking for, and so we would be able to complete that. But notice in this example, we are doing a lot of repetitive work. So for Fibonacci of 5, we actually try to calculate Fibonacci of 4 and Fibonacci of 3. Once again, for Fibonacci of 4, we will try to calculate Fibonacci of 3 and Fibonacci of 2. But notice, all the work that we are doing here, we are also doing over here. Same way over here, we will have to calculate for Fibonacci of 2 and Fibonacci of 1, but we are also doing it from for here and for here as well. So there is a lot of repetitive work, and for every n entity, we are actually doing 2 to the power of n repetitive work, and that's why the brute force time complexity is going to be very horrendous. But needless to say, we can still solve this problem using recursion. So that was our main point. Now let's try to see how we can improvise on the given solution. Now notice that because we are doing a lot of repetitive work, why don't we just try to utilize the most beautiful concept in the computer science, that is dynamic programming. If we use dynamic programming in this case, we should be able to solve this problem very easily, where for any given period, let's say for Fibonacci of 3, if we are trying to calculate the answer, we will calculate Fibonacci of 2 plus Fibonacci of 1. Now for Fibonacci of 2, we will try to calculate the answer for Fibonacci of 1 plus Fibonacci of 0. And over here for Fibonacci of 1, we already have this answer. So since we already have this answer, we don't need to do multiple computation. We can create like a hash map that is going to store the answer based on the Fibonacci value or the Fibonacci key as its key and its appropriate value in the value store, and then we can just simply directly fetch that value. So let's say if we have to calculate the answer for Fibonacci of 5, we needed to calculate Fibonacci of 4 plus Fibonacci of 3, but we already calculate Fibonacci of 3 over here, so we can just fetch that value directly from here instead of doing all of this repetitive work. So that is going to be the idea, and if we apply that, that would bring our time complexity down from big O of 2 to the power of n to all the way from big O of n, because we will just have to calculate the Fibonacci number just once, and we should be able to solve this. Now because we are using an additional stack, or sorry, additional hash map, the overall time complexity is still going to be big O of n, but still that's not too bad. Now there is one more solution where you can also do that in a constant space as well using big O of n solution, but that requires a recursive approach, because sorry, an iterative approach, not a recursive approach. And since we are mostly focusing on recursion as we are trying to learn that, I will not explain it right now, but let me know in the comments if you want to see, and I can maybe post a coding solution for that. So this is going to be the idea. Now let's see this dynamic programming approach in action with the recursive approach, so to solidify our understanding. So now let's see the coding solution. First of all, we are going to define a hash map that we are going to be using to store the dynamic programming approach of memoization, and then we have our fib recursive function that is going to generate the answer. So it takes in as an n character as an input, and now we are going to define the base case that if the given n is equal to 1, we are going to return 1. If it is 0, we are going to return 0. Now we are going to check that whether we have already computed the result for the given n. That is our dynamic programming approach. If that's the case, we can quickly find the answer from our hash map. If we have not calculated, we are going to store the result by calling the Fibonacci of n minus 1 plus Fibonacci of n minus 2. This is going to be our recursive function. And once we get the answer back eventually through a recursive call stack, we will be putting it in the result array or our hash map. And in the end, we simply need to return the result for the original request that gets asked. And let's try to run this code. So seems like our solution is working as expected. Let's submit this code. And the code runs beautifully. It beats 100% of all the other solutions because it is one of the most common solutions, but it's not great in terms of memory utilization because there is another solution that we can use to iteratively solve this problem in big O of one constant memory time, but we are not doing it. Overall, you get the idea that how does recursion work in this. Now let's try to understand the factorial problem. Now we all know what a factorial is. If I tell you that what is going to be the factorial of 3, it's simple. It is going to be the multiplication of 1 multiplied by 2 multiplied by 3 and the answer of this. So it's going to be the answer as 6. Now let's try to put a mathematical equation for our factorial problem. We know that the factorial of 0 is always going to be 1 because of magic, but overall there is a mathematical explanation. I'm not going much deeper into that, but let's assume that this is the case. And then we are being told that for any particular value, factorial of any n is going to be n minus 1 multiplied by n minus 2 multiplied by all the way up to the multiplication goes to 1. So this is the mathematical equation. Now we can clearly see that given that problem statement that you are given value n, you need to find that what is going to be the factorial of that particular value. How would you calculate that? It's very clear that we can use recursion to solve this problem very easily because we are given a particular base case that we can use, that we will have to use, and then we are also given a scenario where the factorial of n is going to be the multiplication of n minus 1 multiplied by n minus 2 all the way up to n. Same way, factorial of n minus 1 is also going to be the same, that is going to be the multiplication of n minus 2 multiplied by n minus 3 all the way up until multiplication of 1. So we will eventually go smaller and smaller in terms of our solution for any given value of n, and by combining the multiple smaller problems we can actually build the solution for the larger problem. So you know that for this problem recursion is a very straightforward approach. Now let's try to think that how would we use recursion in this case. So logically, if we see the brute force solution, it's quite straightforward. Let's say that we need to find the factorial of value number 4. So what we will do is we will try to find the factorial of value number 3 multiplied by factorial of value number 2 multiplied by factorial of value number 1. We can also put factorial of 0, but both factorial of 0 and factorial of 1 is going to be ending up in value number 1. So I'm just putting it as factorial of 1. Okay, let's just presume it that way. Now, same way for factorial of 3, once again we will have to calculate the factorial of 2 multiplied by factorial of 1. For factorial of 2, it is going to be factorial of 1 multiplied by factorial of 0. So again, pretty much the same stuff, and so on and so forth. So we can solve this problem that way very easily. But the thing is, overall we will need to find this value that we need to do. So you can clearly see that this is going to be a 2 to the power of n solution for the brute force approach. We can improve the solution if we use dynamic programming to solve this problem, where we are going to have a hash map that is going to store all the values that we have already calculated so far. Because remember, for factorial of 4, it's going to be 4 multiplied by 3 multiplied by 2 multiplied by 1. So in this case, anyways, we are going to be calculating the factorial of 2 when we do the calculation, or when we would have done eventually. and we would have done it for 3, and when we would have done it for 4. So let's say if I ask someone to calculate me the factorial of 8, then I don't need to do these all of these factorials again, because I've already calculated them previously in the previous step. And that applying the same logic would bring our time complexity down to big O of n, because we are only going to be iterating over all the values of n just once. And the space complexity is also going to be big O of n, because we are using an additional hash map. And anyways, if you use recursion, we will have to use something called as a callback stack, and that consumes big O of n space as well, because recursion needs to hold the values of which function is calling what. Now I'm going to quickly show you the code. This is not a LeetCode problem, but just a general recursive pattern that I wanted to use to explain you. So I'll show you the code, and it runs fine. You can run it for any n number values. So in this case, once again, we have our private hash map that we are going to be using to store the integer values. And we have defined our base case that if the given n is equal to 0 or 1, we simply return 1. And we have our factorial method that takes in any n number as an input. We check within our given hash map that whether we have already calculated the factorial results for that particular n number. If that's the case, we can quickly return. If that is not the case, we are going to have a recursive computation for any value of n. We are going to be doing n multiplied by factorial of n minus 1, and we are going to keep on repeating the same process, and eventually we would put it in the result and return as the result. I've also created a main function where I'm calling the factorial method by n value of n is equal to 5, and this is going to be 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. So the answer should be 120, and which is what we can see, that the factorial of 5 is going to be 120. And I'm not testing with larger numbers, because this can go very easily in the realm of big int numbers, but you get the idea. So the LeetCode problem we are going to do today is called subsets, and we can see that this one is a medium problem and also a very well-liked problem on LeetCode. The statement is quite straightforward, that we are given an integer array called nums, and we need to return all the possible subsets of this given array. So possible subsets means every single possible values or combination of values you can make out of the given array. So let's say that we are given an input element like this, and we are trying to determine that what are all the possible subsets that we are going to be able to make. So we know that for any given n value, we can make 2 to the power n subsets. So in this case, we should be able to make 4 different subsets. Let's understand that what these subsets are going to be. So first subset is going to be quite obvious, that is going to be an empty array, nothing more than that. And because that is a subset of this by default, because if we remove both of these values, still we have an empty array which we are able to generate using this. Next way, we can also generate values just 1. Same way we can also generate value just 2, and same way we can also generate value 1 and 2. So logically, using this logic, we should be able to try to understand that what is the way we can approach this question. And what I am suggesting is that this is nothing more than a decision making algorithm, where at every given step you are making the decision on whether you are going to include that element in your answer or you are not going to include that element in your answer. And based on that, you should be able to come up with these 4 answers. So let me try to explain you my approach using this example, and then we will try to understand this for a bunch of different other examples. Let's say that currently we are given these two elements as part of the input. Now in order to generate the very first subset, we have 2 options. And let's say that we are also iterating over this given input array in this fashion. So the moment we iterate over this input array 1, the very first option we have is that we should we include this 1 in our answer, or should we not include 1 in our answer. So let's generate those subsets. So if we don't include 1, we come up with an empty list. If we decide to include 1, then also we are going to be able to generate a subset like this 1. Same way, next we have the option that after this 1, now the next element in the loop is 2.
So once again we have the same option, that whether we should include this 2 in the answer or we should not include this 2 in the answer. So let's say that if we decide to include this 2 in the answer, then we are going to be dealing with values 1 and 2. Then once again we still have one more option, that is, because remember we are trying to build the subsets, so with every single value we iterate to the next, we are also going to calculate the possibility by removing the previous value. So let's say that we decide to remove this 1 completely, then also we still have one more option, that should we include this value number 2 inside the answer or not. So once again we will have one more subset like this, and then we have reached to the end of our loop, so we don't have any more options. So this logic gives us the correct answer of all the number of subsets that we can make, where what we did is at every given step we check that whether including that value or not including that value would result in some sort of subset, marking those subset in our answer array list we are going to create. And this answer array list is going to be list of list, because it's this array is also going to contain bunch of different array values, and where we are storing the value of every single result that we are calculating. So once again let me try to go and explain this for a broader scenario, the solution I'm proposing, and then it should make you absolutely clear on what is the approach we are suggesting. Basically at every single step we are going to make a decision to whether to include that element or not, and every single answer we generate, it is one of the subsets. So let's say at this very first position we have two options, whether to include 1 as the part of the answer or not to include 1. So let's see both possibilities. If we don't include 1, we have an empty list. If we include 1, we have one value, that is value number 1. Let's say we decide to go down the path of including value 1. Once again we have two possibilities, whether to include value 2 or whether not to include value 2. If we decide to include value 2, we are going to have 1 and 2. If we don't include value 2 and go to the next element, we are going to have value 1 and 3. And that's it. Now these are all the elements we have, so we won't be able to go any further, but we still have a decision to make, which is over here, that after this 1 2, do we need to include 3 or not include 3. So let's include 3. So that is going to be this decision 1 2 3. If we don't include 3, then it is just 1 and 2. That's it. Now once again, now we took care of all the possibilities with value number 1. Now let's try to work on value number 2. So once again we have the possibility of including 2 or not including 2. We already calculated if we don't include 2, then it is going to be an empty list. So let's include 2 now. So by doing that we are going to have one decision tree like 2. Now at this 2, once again we have two possibilities, include 3 or not to include 3. So let's decide to include 3. Then we are going to have value 1 2 and 3, and that's it. If we don't include 3, we already calculated that possibility over here. And last one is value number 3. So once again for this value number 3 we have two possibilities, whether to include this 1 and 2. We already calculated all of these by including 1 and including 2. If we don't include 1 and 2, then we only have one possibility, that is to have value number 3, and that's it. So these are at every single decision that we are able to generate, we are able to see that what are the values being generated by those decisions, and all of these are actually the answers or the subsets that we need to record. And that's it. This is the crux of the entire problem and the whole solution. So we can see that we are being able to generate in total these 8 values, and these 8 values are actually the answer we are looking for. Now let's try to think about that how did we generated this answer. The logic is quite simple. We do this recursively and using backtracking. And how do we do backtracking and recursively? Let's understand this with, first of all, what is the recursive pattern. So we know for recursion we need two items. First one is a base case and second one is a recursive function. So base case is quite obvious, that whether we have executed all the possibilities or we completed every single elements. So both of these base cases works perfectly fine, because at every step we would be able to generate an answer. So this is our recursive function, that whether we exhausted all the possibilities or we don't have any more elements that we need to traverse over. Now what is the recursive function? It is also quite obvious, that as long as any particular elements exist, then once again record both possibilities of including that value and not including that value as part of the answer After doing that, once again do a recursive call back to the same function in order to check that if you include that value, then also what are the remaining values persisted. Call back the recursive function with those values. Once again, if you don't include that value, what are all the remaining values persisted? Once again do a callback operation, and if there are no other values left, then basically just do a return call. So this recursion would be able to generate the answer. Now why do we need to do a backtracking? And that is also quite obvious, because what we are doing is that we are building a decision tree. So let's say that we are given this values 1, 2 and 3. So once again, we first check all the possibilities for this value number 1. So we check the value number 1, then we check value for 1, 2 and 1, 3, and once again we check for value 1, 2 and 3. And after, at this moment, we will once again have to go back and see that did we miss out any particular element or any particular possibility that we did not check. So far we did not, we checked all the possibility over here, we checked all the possibility over here. Once again we do a rollback. Once again we check, did we check all the possibilities? Yes, we did. So once again we do a backtracking and go to the next element and once again repeat the same operation. And that's why backtracking is the backbone of this problem that allows us to solve this problem flawlessly and pretty smoothly. So this is how we are going to be able to use solve this problem using backtracking and recursion, and these two typically go in hand. Whenever you try to solve some problem using backtracking, most likely doing it recursively would make much more sense. We already know what is going to be the time complexity in this case. That is going to be big O of n multiplied by 2 to the power of n, because that is all the possibilities we will have to check. Now let's quickly see the coding solution. So coding solution is quite straightforward. First of all, we have our subsets class where we are receiving a nums as part of the input. Then we are generating a list of array list to store our result. And then we are going to call our recursive method that we have created, that is called generate subsets. Now we are passing in the current index, the starting index. Then we are passing in the nums array, and we are also passing in a variable to store our result. And also we are passing in a new array list or the current array list that we are going to be creating, that we would be adding at every single subset iteration. Now let's see our helper method. So first of all, the moment we enter inside our subset, we are first of all going to add whatever the current array list that we have been able to generate it so far as part of our result as a new instance of the array list. And then we are going to have a for loop that is going to simply iterate over every single index position inside our nums array, where we are going to check for the following. First of all, we are going to add the current value as part of the current iteration that we are building, which would be added into the array list or into the result in the next iteration of the recursive call. Then once again, after adding the current value, we are once again going to call the current value as part of the result as part of the recursive call, and this is our recursive function. And after that, once that is done, we are going to be removing the current element in the next iteration. Why? Because let's say we are dealing with 5 elements, then at every given instance we need to remove one element after we are done iterating every single possibility at that value. So this is that step, and that's it. So by the end of this array, every single value should be populated inside our result array list that we have been able to create it. And at the end of this recursive call is done, we are simply going to return that value. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions, and also it is excellent in terms of memory utilization as well. So once again, the solution of this code is available on our GitHub repository, so you can go and check it out from there. Thank you. Now we are going to be solving the problem subsets 2. Now this is very similar to our original subsets problem, but there is a slight difference. Now we can see that this one is a medium problem and also a very well-like problem. The problem statement is that we are once again given an integer array nums that may contain duplicates. So we need to return all the possible subsets plus we are told that the set must not contain duplicate subsets. So there is only just one tiny bit of difference. Now let's first understand that what does a different subset means. So let's say that we are given an input array like this, then the number of subsets it can contain is going to be 2 to the power of n. So where n is the given number of elements. So in this case we have 2 elements, so we can expect that 2 to the power 2, which means 4 subsets we should be able to create. And these 4 subsets are going to be an empty list, a subset only containing value number 1, a subset only containing value number 2, and a subset containing value number 1 and 2. That's it. So this is the whole solution. But the thing is, I know we just solved this problem in like our subsets problem, so if you want you can check it out from there. The thing is, in this case, the only difference is that let's say that we are given a value like this, where the input may contain duplicates. Then this changes our equation a bit, because in this case, we need to only return the unique subsets. So in this case, if we want to create the number of subsets, definitely we can create 2 to the power of n subsets. The issue is that we can create a subset, we can create like an empty subset, then we can create a subset with just one. But once again, if we try to create a subset with this 2, let's say, then we can also create a subset like this 2. And if we were to put both of these in the answer, then there would be duplicated entries. So we only need to just pick one. So that is number one thing. There can be one more duplicate in this case, and that duplicate could be that we can create a subset like this, value 1 and 2, and we can also create a subset like this where value is 1 and 2. So if such kind of situation occurs, then we need to take care of that scenario. So basically making sure that whenever we have duplicated entries, we just have to keep them aside or not consider them for the current part of the subsets. Now we all know that what was the strategy we used in order to calculate the subsets. Let's say that we only have just 2 values given and we are trying to generate the subsets. Logic is quite straightforward. We are going to be using the backtracking. On top of it, we are going to be using recursion. Now what is going to be logic for our backtracking? That while after calculating every single path for every possible subset, then we are going to be doing a backtracking and once again repeating the same operation. What do I mean by that? Let me just explain. So first of all, we are at the empty list position. Now over here we have the possibility to include this value 1 or not to include this value 1. Same way we have the possibility to include this value 2 or not to include this value 2. Let's say that we decide that we are not going to include both of these 1 and 2. So in this case, we can create a subset like this, like an empty list, and we will mark this as part of the answer. So let's say that this blue line indicates that we already marked it as the answer. Now, once again, after marking this answer, we still somehow needs to go back and revert our operation. So in the previous choice, we decided that we are not going to select this value number 1, but now let's say that we do decide to go ahead to select this value number 1. So once again, we can create a subset where we are only selecting the value number 1. So once again, this is also part of the answer. So I'm marking it with a blue line. But after doing this, once again, we will have to do a backtrack and see all the possibility. So we already exhausted all the possibility of selecting one and not selecting one. But the thing is, we haven't exhausted all the possibility of selecting 2 and not selecting 2 along with this one. So let's say that along with this one, we have the possibility that whether we select 2 or not select 2. So we not selecting 2, we already calculated. But now we are calculating one more possibility where we are selecting 2. So we have values like 1 and 2. Okay. After doing this, we can do a backtrack. We check all the possibility at 1. Once again, we check everything so far. The thing is, we haven't checked the possibility of only considering 2. So once again, we are simply going to be considering 2, and this is going to be our backtracking mechanism. On top of it, this is also going to be our recursive function that I just explained, where for the recursion we need 2 items. We need a base case and we need a recursive function. So for the base case, it's quite straightforward that whenever we create or we make any single decision, we simply add it to the answer, and this is our base case. After this, for the recursion, we go back to the next recursive call with that selected value or not selected value, and once again repeat the same process for the next upcoming remaining elements inside the array. So this already makes sense. We already do this. But the only issue in this case is that we simply don't want to consider, let's say that we are given values 1, 2 and 2. So now in this case, once I'm making the decision, let's say I put down the empty array, then I put down a list with 1, right? Now at this 1, I have two possibilities. First possibility is that I'm going to be considering this 2, and second possibility is I'm not going to be considering this 2. So let's say I decide to consider this 2, then I should be able to create an input array like this, or like a new subset like this. Once again, let's say that I go to and let's, for a simplicity, let's assume that this value is currently 3, okay, not 2. So if this value is 3, then I create one possibility where I'm considering 2. I can also create one more possibility where I'm not considering 2, which means there can be a subset like this 1, 3. But in this case, rather than this value being 3, this value is also 2. So it's the same value. So if I try to do this possibility in this case, then I'm just stuck. I'm left with only this value. So what I can simply do is that I can take the given input. Let's say the given input array is like this, but it right now it is already sorted, but it is possible that this may not be sorted. We could have given values like this. So once again, if we want to do the solution, what I'm suggesting is that whatever values we are given, we simply sort those values. So let's say we get a nice looking values like this. After sorting, all we simply do is we check that at any given moment, whenever we calculated a possibility with this 2, now we are trying to calculate another possibility. We just check that the current element we are considering for the possibility, if that element is same as the previous element, then we just don't consider that possibility. That's it. This is the whole solution. So now what would happen in this case? We will have an empty list. We will have value with 1. Now we will have one more subset with 1, 2. Now after this 1, 2, we still have two possibility whether to include this 2 or not to include 2. So let's say that we decide to include 2. So then we still have one more subset like this. So we also consider that. After this one, we are doing our backtracking by removing the last element added. We do the backtrack. We don't need to calculate this one because we already know that it's the same element. We go back to 1. We check all the possibilities with this 1. So now we are at this position number 2. So we decide to include 2 only. This is a new subset. We add it to the answer. Now after at this 2, we have the option that whether do we need to add this value or not to add this value. So this value is quite straightforward. It's 2, 2. It's a new subset. So we haven't calculated that. So we can simply add this one. Now after calculating this, once again we do a backtrack. Now at this backtracking location, now our time is to move to the next element and not consider this one. But once again, while making a decision for this one, we check that whether it matches the previous element. Yes, it matches the previous element. If it matches the previous element, what is the point of considering this for the subset? So we are not going to do that. And that's it. This is the whole solution. And if you see the coded approach, it would make much more sense. Plus you already know that how does the calculating subsets work, because we already saw that in the past, that the whole explanation and the whole 9 yards. I just re-explained the whole thing, and I also explained that why we are adding this tiny logic to our already beautiful solution. Now let's quickly see the coding approach. So very first thing we are doing is creating a new array list where we are going to be storing the results. Then we are simply sorting the given input array. And then we are calling our backtrack recursive helper method where we are passing in the new result, where we are going to be storing the array list of lists, and we are passing in the new instance of the array list to store the current list that we are iterating over. Then we are going to be passing in the given input nums, and we are also going to be passing in the starting index where we are looking at. So initially we are starting from the index 0. So we are just going to pass in 0. Now let's see our helper recursive method. First thing we are doing is whatever value we have in the current list, we are adding it into the answer. So during the very first call, we are adding just an empty list into the answer as well. Next, we are running a for loop from the start to the end of the given array. Plus, we are just checking for a very simple condition that if the given input I is greater than start and the current element is equal to the previous element, if this is the case, we simply continue. If this is not the case, then we simply add the value to our current array list. Then once again we call our recursive function. After the call comes back from the recursive function, we remove the very last element added inside the current array list, and then we repeat the same process until we are done with the entire for loop. And this should populate our results completely. So now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs beautifully, faster than all the other solutions, and also best in terms of space complexity. So once again, the solution is present at our GitHub repository, so feel free to go ahead and check it out. Till then, thank you. Now the LeetCode problem we are going to solve is called permutations, and we can see that this one is a medium problem and also an extremely well-liked problem. The statement is quite straightforward, that we are given an integer array called nums of distinct integers, and we need to return all the possible permutations that we can make. And for good thing for us is that we can return answer in any order. So first let's try to understand this with few examples. Let's say that in the input we are only given one element, then we can only generate just one permutation. So this is what we need to return. But if we are given more than one element, let's say 1 and 2, then we can actually generate two permutations in this case. First permutation is going to be the same value as it is. In the second permutation, we are going to have the values being flipped around between 2 and 1. So these two are the permutations that we need to return. Let's take one more example. Suppose in the input we are given the values 1, 2 and 3. Then we can basically calculate that we should be able to make 6 permutations in this case. Why? Because for any particular given numbers, you can make n factorial permutation. So in this case we are given 3 elements, so 3 elements is going to be 1 multiplied by 2 multiplied by 3, as in 3 factorial. So in this case the answer is going to be 6. Now let's see that what are all these 6 elements are going to be. Well, so these are all the 6 permutations we can make. Now logically this is nothing more than a decision making element or decision making algorithm, because over here we can see that if we have to make permutation of this element, let's say that I have 3 blocks where I can fill in values. Now let's say for some reason I decide to put 3 in the first block. Then I know that I still have 2 values where I need to fill out something, but the thing is I can only fill out between this value 1 and 2, not this value 3. So once again I can repeat the same process, and let's say randomly I decide to pick value number 1. So now for this last element I only have just one possibility, and that is to fill in this value number 2. And this, the moment it reaches to the length of this previous one, we can determine that this is one of the permutation that we can store as part of the answer. Now after storing this, we need to check that whether keeping this 3 over here at the beginning, are we leaving out or being done with all the permutations? No, there are still possibility of permutations left. Let's say that we decide to eliminate this value number 2 over here and this value number 1 over here. Now once again, keeping this 3 on this place, once again we have the option that instead of selecting 1, we can actually select 2 over here, then we will have 1 over here, and this would be a new permutation. So visually this is very simple to understand that how does this function, but the thing is implementing this is slightly tricky. So what I'm suggesting is that we actually use the same algorithm that we just saw, but we apply it using the logic and possibility and concept of backtracking. Plus on top of it, after using the backtracking, I also suggest that we use a recursive approach to recursively recall the same function with different inputs. And why am I suggesting this is because number one, we already know that we are repeating the same process. All we are doing it is that the input we are given, we are picking one value in, we are marking that particular value with one of the values, and for that let's say that over here we have 1. So once again now we have two possibilities. First possibility is that on this place, for the second place, we can fill in the value 2 or we can fill in the value 3. Once again, let's say if we decide to fill in value number 2, then we are only left with just one possibility for this last element, that is this value number 3. And this whole path defines one of the permutations. So this we will be able to mark as the answer, and then if we decide to go down this path, once again the values are going to be 1, 3 and 2. So this is going to be our second permutations, and once again we can mark this answer as well. So now let's say that what are the things we need to solve this problem and how we are actually going to be doing that. I just explained that we are going to be using backtracking plus recursion. So let's say that what do we need for our backtracking function? The idea is quite straightforward, that we will keep on going in one direction until we reach to the length of the given input. Once we reach to the length of the given input, we will mark that entire path in as part of the one of the answers, and we would put it into our list of lists that we have created to store our answers or results. Once doing that, the idea is to once again do a backtrack, and after doing the backtrack, once again see that what is the potentially different path that we could have taken, and once again once we reach to the answer, we basically store that answer. Now there are two critical parts in this case that we will have to consider. Number one thing is that we will need to know at some point that what are the values we have already calculated and what are the values we have not calculated so far. So what I'm suggesting is that let's say you decide to put 1 over here, then I would need some sort of way for my computer to tell me that this 1 is already part of the function. So for that I'm suggesting to use a used array, or like array named use, and the moment we add any particular value inside the current consideration for our recursive function, we are going to mark this used function as true or false. So this would be my used array of boolean values, and currently I would mark that this is true, which means I'm currently considering 1. Then once again, let's say that now I know that through my used array I only have 2 more possibilities left because this 1 has already been filled. So for the next element, I'm going to consider this value number 2, and once again I'm going to mark this value 2 as being used as one of the decisions. After doing that, once again I'm going to mark this value 3, and then I'm going to mark this 3 as being used. But the thing is, because I reached to the end of the list, so the moment I reach to the end of the list, I can mark this answer 1, 2 and 3, and after marking this answer I can actually go back, and I can go back in time with my recursive function and say that over here, instead of using 2, now I have decided to take another path where I'm going to be considering 3 as part of the input. And in order to do this one, I will need to constantly update this used array. That is number one thing. Second thing is, in order to calculate this path, I will also need to have a current array or array list to store this path as well, that these are the values we are currently iterating. And the moment we identify that we have reached a new answer, then for the next iteration of the recursive call, I simply need to regenerate the entirely new array. So I know my solution might confuse you a bit, but let me just give you this with like using 2 examples. So let's first quickly take the example of simple 1 and 2 values. Okay, the logic is that we are going to have a recursive function that is going to store. So for the recursive function I did not explain, but basically for the recursive function we need 2 items. So we need a base case, and we need that what is going to be our recursive call. Base case is quite straightforward, that the moment we identify that our given current n or the current length of the given input is equal to the original n of nums, then we have found the correct path. In this case, we would mark the current path inside the answer, and after marking that we would basically return. So this is going to be our base case. Now for our recursive function, the idea is quite straightforward, that we are going to pick one element right now, and through that one element we are going to be marking the used array for that particular element to be true, and then we are going to call the recursive function once again with the remaining portion, because we still haven't identified all the values. Once we identify all the possibilities and we receive an answer back, then we are going to eliminate the last element we had inside our recursive function to be turned out to be false, and keep on repeating that in order to calculate other possibilities. So let's first see for this example. The idea is that first of all over here I have two possibility. Let's say I mark number 1 element as being used, and I have a current list where I'm going to store that what is the current path I'm taking. Okay, I took 1. Now I'm once again going to call for the next element. So now I call for the next element, that is obvious choice 2. So I mark 2, and now I know that my length of this current has reached to the n. So I'm going to mark this as part of the answer 1 and 2. After doing this, once again I'm going to do a backtrack call. During the backtrack call, I'm going to mark this 1 as not being used and 2 as not being used, and then I'm going to be iterating over this given input in this fashion. So I already took care of this element, and now I'm going to start taking care of this element. So now I have my 2 as being used. Now I have my new current instance being created where I'm starting the path from 2, and I'm going to go down to the next path. So I only have one possibility, that is to add value number 1. So I'm going to add value number 1 over here, mark 1 as being used, and because this n is correct, so once again mark the another answer as 2 1, and now I have my answer that I was looking for. So after this, I realized that in my existing loop, I already be done through all the elements inside the given input. So which means now whatever I have in the answer, I can simply return that. So now if you want, you can directly go to the coding approach if you already understood what I meant. If you didn't understood, then let me also do the same iteration for this path as well, and once again repeat the same procedure. So logic is, we are going to be iterating over every single element one by one. That is number one thing. Next thing is we are going to have our current list or the current values we are iterating over, and we are going to have our used array where we are going to be storing that which are the elements we have already used so far in the current iteration, and we are going to be updating the values one by one. So let's say that in the current path I add value number 1, so I'm starting the path from value number 1. After 1, I decide to add value number 2 as an input. So once again I do that, and after this 2, I add value number 3. So the moment I add value number 3, my length is equivalent to so I'm going to store the answer 1 2 3. After storing this, now once again I do a recursive call. So I basically break out, so which means I will have to remove the last element I added. Still keeping 1, I still have one more possibility that I haven't tested. So once again I'm going to mark 3 as being visited. So now I'm going to take one more path, and by the way, this is going to be a new instance where currently the nodes I have visited are 1 and 3, and next time I'm going to be visiting the value 2 because that element is left over here. So once again I'm going to be marking 2, and I'm going to have one more possibility 1 3 and 2. Once again now I do a backtrack. So backtracking would make sure that I took care of 3 over here, I took care of 2 over here, and all of these things are done. So now my used array is being backtracked to all the way to the beginning. So now once again I'm going to repeating the same process, but now this time with value number 2, and keep on doing this recursively until we reach to this very last element 3, where we have all of the 6 possibilities calculated, and this is the whole solution. So now let's quickly see the coding solution, and that would make much more sense. Now first thing we are going to do is that we are going to create a new array list which is going to store our results. So now you can see that this one is an array list that stores different array list inside. Then we are going to initialize our used boolean array in order to keep track of that what are the current elements we have already used. And then we are going to have a helper method called backtrack, where as an input we are providing our result that we have calculated so far. Then we are going to have a new instance of an array list where we are going to be storing the current elements we are iterating over. Next, we are going to be passing in the given input nums, and lastly we are going to be passing in the new used array that we have created. Now first we are going to be checking for the base case, that if the current size is equal to the length of the original given array, then we are going to add the results of the current array list inside the new instance of a new array list, and we are going to be doing a simple return. If that is not the case, then we have our for loop that we need to iterate over. So very first thing we are doing is that we are starting from the 0 and iterating I until we reach to the end of the array. Then we are first of all checking that if the given I value is not used, then we are going to be adding that value inside the current path that we are iterating over. So we added that. Then we are going to be marking that particular element as true inside our used array. And after that, we are going to be calling our backtrack method recursively, where once again, we are simply providing the results that we have calculated so far, the current path, which now contains a newly added element, and the nums input, and the used array that now contains that the current element is being used. And that's it. Basically, this should ensure that all the work gets through, and the moment the list size is correct, then we would start adding those values inside the result. But the thing is, after the backtrack call, we will also have to remove the lastly used elements. So we are going to be doing that, and we are also going to be removing that value, the very last value that we had in our current list. So we are always updating that in order to calculate new possibilities. And this is the whole solution. Now I know it's hard to visualize, but coding is very small, and also you can understand that how to generate it on a pen and paper. So you can just work around with different examples and it would make sense to you. Now let me quickly run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs super fast compared to all the other solutions, which means this is an excellent approach. Now I know using an extra used array might hamper with our space complexity, but this is still a much faster result. So now I will be posting the solution in our GitHub repository, so you can check it out from there. Thank you.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, and I have provided the introduction of what are the things to expect from this video. We are going to solve the combination sum problem, and first of all I'll be showing that what are the top companies that have recently asked this question from LeetCode Premium. We'll understand the problem statement, we'll also find the optimal solution, and we will also determine that what would be the intuition behind it. We will create an example and we'll walk through it, and at the end I'm going to write a Java code. I'm going to explain it thoroughly, that how we come up to it, and also we would be explaining the time and space complexity. So first of all, these are the top companies that have asked this problem recently, and if we see from past 6 months to a year, it's eBay, Google, Goldman Sachs, and these companies. And pretty recently, Amazon has asked this question 20 times in its interviews. Facebook has asked this question 18 times in its interviews. So I highly suggest you to take a look at this problem, understand it completely, and then practice it as much as you can. This is a medium problem, and we are given a distinct integer called candidates, and we are also given a target integer, and we need to return all the unique combinations of candidates where we can reach up to the target value. Now this is a little bit tricky part to find all the unique combinations for this target candidate, because let's try to understand this with an example. So over here we are given the candidates as 2, 3, 6 and 7, and we need to reach the value number 7. So we can clearly see that 7 is already present over here, so we can return this one. The thing is, we need to return all the unique combinations. So one unique combination is 7, second unique combination, and also one more thing, we can use the same number from the candidate unlimited times. So if we apply this theory, then we can find another value that can reach to the sum of 7, then that would be 2 plus 2 plus 3. If we do that, this also sums up to 7. So we need to return a list where the two values are 2, 2 and 3, and the second element is just 7, and this would be our solution for this given problem. Okay, let's try to understand this problem with a custom example, and it is really important to create your own custom examples because it shows that you have the ability to think outside of the box, and you can create test cases on your own. It is a really important skill to have for any engineer, and especially FAANG engineers. So we are given 3 candidates, 2, 5 and 6, and we need to see that what are all the combinations we can get out of these candidates to achieve the target value 8. Now just by looking at it, we know that the two combinations we can create is 2, 2, 2, 2. This is one combination, and the second combination we can create is 2, 6, and this would be our answer. The thing is, let's see that what would be the most basic solution we can come up with, and what would be the intuition behind it, and based on that we would be able to create an algorithm that would solve this problem. So initially we are at this position 0. Now at this position 0 we have 3 possibilities from which direction we can go. We can either go to this value number 2,
we can go to the value number 5, or we can go to the value number 6, because these are the three candidates that we are given. And also we should not forget that the target value we want to achieve is 8. Okay, so keeping this in mind, we need to go and pick a side where we need to go further and keep going. So again, let's just go on one direction for all the cases we can. So over here we are at 2. Now remember that we can use same element infinite times, which means that there can be one possibility as 2 2. Of course, there can also be one possibility as 2 2 2. Of course, the thing is, uh, notice that we need to put a constraint for the number of decisions we are making, and the constraint is that if at any point the direction where we are fetching all the candidates, if the sum of those can either be less than target, they can either be equal to target, or they can be greater than target. These are the three possibilities we can have. If it is less than target, which means that there is still room for us to find the potential combination, which means we can keep further going on that direction. If we are already at value number 8, or whatever target we are, we can directly put this value in the result. But if we and which means that we have found the combination, so there is no point in going further after we have already found the combination, because all the elements, they are only going to add up to whatever combination we have, which means that we won't be able to find another combination with the same numbers that were used to achieve this equal to. And the third option is that the value could be greater than 8. If it is greater than 8, why are we keep on going or to do more iterations and putting more strain in our computer? There is no point in doing it, because we could have infinite options, and if we do it, this would be like the this would be like the best way to deplete the resources of our company. So we don't want to do that. So now, since we have kept these things in our mind, now let's see that how can we use them over here. So far the sum we have found up until this point is only 2. But the thing is, over here we have 2 candidates, and the sum we have found so far is 4, which is still less than 8. This is 6, again still less than 8. Now over here we can have one more possibility as 2 2 2 and 2, and if we do the sum of this is 8, which means that this is actually equal to whatever the target value we had. So we can add this to our result combination. We would have that we have already find one value in our result, and we will just add it as 2 2 2 2. This is one combination that we have found so far. The thing is, we are not done yet, because we still have other candidates that we need to look at, and we need to check the possibilities. But the thing is, we have concluded at least one thing so far, and that thing is we can't go further down on this path, because all the values would be greater than 8, and which is not what we want. So the only way we can go is actually we can go back and see that have we missed out on any combination. So over here, the next possibility we can get is we have already used 2 as our candidate for this value 2 2 2. So the next possibility we can have over here is it could be 2 2 2 and 5, or it can be 2 2 2 and 6. So let's do sum of all the combinations. So some of these combinations would be 11, and some of these combinations would be 12. Notice that both are actually greater than the value of our target, which means that we can't go further down at any of these positions, and we have exhausted all the possibilities up until this point. So since we have already exhausted the possibilities up until this point, the only way we can go is we can go back. At this position 2, we have exhausted all the possibilities there can have. One, we found the answer, and the other two we found that it cannot be part of the combination, which means that we have already exhausted all the possibilities for this value 2 to 2 as well, which means that we can't go down, but we can go up. So over here, have we exhausted all the possibilities so far? No, there are still room, there are still other possibilities that we can check. So let's do that. So one possibility we can have over here is 2 2 2, which we already checked. The next possibility could be 2 2 5. and the next possibility would be 2 2 6. So sum of these values is actually 9 and sum of these values is actually 10. Again, both are greater than whatever the target value we had, which means that we cannot go down, so we will go back. We went back. Over here we check that we went through all the possibilities, which means that we are done over here, so we can't go down any further on this path, but we can go up. So if we go up, we ask ourselves a question that have we explored all the possibilities this at this position? No. The possibilities we could have is 2 5 2 6. So let's take this value first. So at 2 5, the current sum we have is 7. 7 is less than whatever value we have as our target, which means that we still have possibilities. The possibilities we can have is 2 5 5 or 2 5 6. Notice that over here we only had two possibilities where we can calculate it from. We did not had the possibility of 2 2 5. Why? Because we already calculated it for this portion over here. Remember, in the previous iteration we already calculated for this scenario, which also shows one very important property, and their property is that out of our candidates, whatever the candidates we are given, if we are at any particular position or any combination of positions, so whatever value we have as last, we can only use that multiple times, or we can use the values that come after it. We cannot go backwards because we have already exhausted those possibilities in an iteration before this, as I showed you earlier, that this we have already explored over here, and this 2 to the 5 2 5 we are exploring at this position 2, which means that the only combinations we can make up after this point is either 2 5 5 5 something blah blah blah, or 2 5 6 6 6 something like this, but we can't make like 2 2 2 5 because we already checked that over here. So, and this is a very important property that we are going to use. Okay, at this point the sum we can have is 12, which is greater than 8, so we can terminate over here. We can't go down any further. And over here the sum would be 13. Again, we can terminate over here. We can't go down, which means we have to go back. So we come back at 2 5. We say that okay, we have explored all the possibilities over here. We go back to value number 2. Now the thing is, at value number 2, have we explored all the possibilities? No, there is still one possibility pending, which is 2 6. So at 2 6, this value, the sum would be 8. Again, this is really critical because we have found a pair that equals to whatever target value we had, which means that we will add this combination to our result list. So over here we will add another entry 2 6, and after adding this, we have explored all the possibilities after this point, which means that we would go back. Now at this position 2, we have explored all the possibilities it could have, and because we have explored it, we will again go back to our 0th position. The thing is, we are still at 0th position, so can we stop now? No, we can't stop because we still have a whole lot of possibilities that we haven't touched so far. Because remember, over here we still have this 5 and 6 pending. So let's see that what could be the possibilities over here. Now at 5, again we can only have two possibilities. As explained earlier, we could have either 5 5 or we could have 5 6. So let's do the sum of these values. So 5 5, the sum is actually 10, and 5 6, the sum is 11. Both are greater than 8, which means that we can terminate over here. So that concludes that at this position 5 we ran out of the possibilities. We went up. At this position we are done. So again we go back. We go back at 0th position. We check that do we have any other options where we can explore, and yes, currently we are at value number 6. So 6 is again less than our target 8.
so we can go further from 6. The thing is, at 6 we can only do 6 6. We can't do any other combination because those we have already checked so far, which means that 6 6 the value is 12. So 12 is already greater than 8, which means that we can't go further from this, which means we can't go further. We go back. At 6 we see that have we explored all the possibilities? Yes, we have explored all the possibilities, which means again we go back to this position 0. So at this position 0 we check that now have we explored all the possibilities? Yes, initially we check all the possibilities for the value 2, again we check for value 5, and again we check for value number 6, which means that even at 0th position we are done. So our base case has satisfied. Now whatever we have stored in our result result list so far, we can simply return this, and this would be our final solution. And this is actually the optimal solution that we can achieve. Notice over here that we are doing lot of repetitive work. At any position we were calculating the different possibilities we can have. We are picking a possibility, we are exploring in that direction, depth first search. We kept on exploring. Once we found a terminating case, once we found a terminating case, we would go back to a point where we can still explore for more possibilities. Over here again we would further go down to additional possibilities. We would find a terminating case, again we would come back, and eventually we would come back to the 0th position from where we started, and after the calculation we will return our result. So this, where at any point we are coming back from where we originally started. This is actually called backtracking. This is a really important concept in computer programming, and I just showed you that how can we use it, and that is why, because this concept is really important, it has a lot of very practical applications, and that's why you see that why all those big companies like Google, Facebook, Amazon, Goldman Sachs, they were interested in asking this question to their candidates, because they want to know that are you familiarized with very important things that are really critical, and can you go down that path. And yeah, so since we have found our optimal solution, I did not mention explicitly that I was showing you the optimal solution, but the thing is, I told you that this is the intuition behind it, and once we knew the intuition, we just need to find a way to implement it in computer programming. The way to implement this, you must have guessed it correctly, that we were doing so much repetitive work again and again, and if we were using it somewhere, and we had some terminating conditions that either if the value is equal to or greater than our target, we would terminate, which means that we were using recursion at its best over here. So yeah, this is basically our solution. So let's calculate the time and space complexity. That time complexity for this one would be big O of n to the power t. Now first let's determine that what this n and t means. N is actually the number of candidates and the least value for this one, and t is actually the total amount, because imagine that what could be the longest sequence we can have at any given position. Well, suppose our target value is 8 and our candidate is 1, which means that we would do 1 plus 1 plus 1 up until 8 times till we get the value 8, which means that we need to go in one direction 8 times, and at any position we can have multiple options or we can make multiple decisions, and from further down we can go ahead, which means that we need to do this work n to the power t times until we find the solution. So that's why this is the time complexity. So first of all, we'll create our result list, and now we'll create a list to store the current combination. Okay, now we'll create a backtrack method, and this would be our recursive method. So initially we are going to provide the target result combination 0 as the starting point and the candidates array. And after whatever the result we get back from that recursive call, we simply need to return whatever we find in this result list. So let's create the recursion method. Okay, so first of all we are going to create the terminating cases. So if target is equal to 0, which means that we have find a combination that sums up to the target value. So we can just simply return it to we can simply add the combination to our result. If this is not the case, we need to return we need to check that whether the target is less than 0, which means that we have already surpassed our target and we need to break. So we can just return null. If both cases are not true, which means we still need to look for our combination. So we'll start by checking in our combination from the position start, and we'll go until we still have candidates. Now inside the loop, first of all we will add whatever candidate we are currently looking for in the our combination list. Okay, after that we can do our recursive call. And as a target, we will have target minus whatever candidate value we found. And start would be ith position. And I think that would be it. Yeah, one more thing, we will have to remove the entry from our combination list, because we will be doing backtracking when we move towards the next value. And I think this would be it. Let's try to run the code. This should have worked, but I don't know why it's not working. So we'll just enter the value manually. Oh, it should be candidates. Okay, our solution seems to be working. Let's try to submit the code. And yeah, our solution works perfectly fine. And I would be posting this code in the comments. You can check it out from there.
Now we are going to be doing an awesome LeetCode problem that is called combination sum 2. This is the subsequent question to our original combination sum problem with some slight tweaks. Now we can see that this one is a LeetCode medium problem, but in my opinion this can be categorized as hard problem sometimes as well, because combination sum in itself is slightly tricky to understand. And we can see that this one is a very popular LeetCode problem, also being asked at tons of companies. Basically we are given a collection of numbers called candidates and we are given a target number. Now we need to find all the unique combinations in the given input array such that the sum of those values is equivalent to the target value. There can be more than one results, so we need to consider all of them. Now we are told that each number in candidates may only be used once in the combination, and we need to make sure that the given solution set must not contain any duplicate combinations. Okay, so now let's first try to understand this with an example. We are given this candidate array and we are given the target value to be 5. Now next thing is that we need to generate the unique sets. Now let's see that what are all the combinations that can generate this value 5. We can see that we have value 4 and we have value 1. So 4 and 1 is a combination that can sum up to value number 5. So that this can be one of the potential answers. Next one is we have value 2, 1 and 2. So once again we can generate value like this, and this can also be an answer. Next value is that we can do 3 to 2. This is also one of the subset that can generate the answer. But now there is one problem over here. We also have this 3 that we can utilize with this 2 to once again generate the target value 5. The thing is that value is also going to be 3 2, which we have already entered in our result. So we should not be reusing the same set in our results, because we need to make sure that this answer becomes unique. So if we, by considering these elements, we can only generate these 3 values or these 3 sets that combination to the total value 5. So we need to understand that this is how we need to solve the problem. So now let's try to see that what could be the potential solution over here. Now the logically, the very first thing that it would make sense for us to do is that instead of treating all of these weird values side by side randomly, it would make much more sense to, number one, sort the given input array. Why am I suggesting to sorting the given input array? That has two reasons. Number one reason is that let's say that we have some values like let's say 10 and 15 and then so on and so forth, like 100 other values, okay? And we are given the target value to be 5. So the moment we reach to a value 10, then why do we even have to check possibility for all of these 100 values if we have already sorted the results? We know that all the values sum is always going to be greater than 5, which means it is going to be shortening the reach we will have to search for. That is a good benefit. Second benefit is that it will allow us to handle the duplicates in a more elegant manner. So what I'm suggesting is that let's say that in this case, we have the values 1, 2, 2, 3 and 4. This is the input we are given. Now what we are doing is that logically it's very simple. We are just simply making decisions. And what is the decision we are making? We are iterating over the very first element. Okay, so let's say that we are currently passing through value number 1. We know that the target has to be 5, but our current sum that we have made so far is just value number 1. So we will need to add some more subsequent values. So let's say we decide to add value number 2 down this current path. So now the sum is 3, still less than 5. So once again we decide to add value number 2. So after adding this value, our sum becomes 5. So the moment our sum becomes 5, whatever the values we were currently having as part of our path, this is one of the potential answers. So let's mark this as part of the answer. Okay, that we currently have found one of the combination 1 to 2 as part of the answer. After doing this, there is still more possibility that we could have some other value that we might have missed on. So we will have to backtrack and once again see for other possible answers. So let's say that we do a backtrack at this position number 2, and once again this now the problem comes because this next element is already 2 and we just did a backtrack. But the thing is, we already considered this 2, so now we will have to consider value number 3. Okay, so let's say if we try to do this one, this current sum becomes 6. So the moment current sum becomes 6, we know that this is no longer a viable solution, which means we will have to do a backtrack because this solution is leading to a value greater than 5, and once again we will have to repeat the operation for all the other remaining possibilities. So we remove value number 2. So once again, now with this value number 1, there might be some other solution with 1 and 3 that we could make. So we try to add value number 3. After this value number 3, the current value is 4. After 4, we add value number 4 over here. So doing this also brings our sum greater than 5, which means we will have to do a backtrack. We do a backtrack and we get rid of this value number 3. Now at this value number 1, we still have possibility to check for value number 4. There is still one more decision we haven't made. So let's say we do this one. The sum of this is actually 5, which means we found another set that corresponds to our correct result and our correct instinct. So we are going to mark this as part of the answer as well. Now once again, we know that we took care of all the things we could using this value number 1. So now we are simply going to go to the next element and not even consider 1 because we ran through all the possibilities we could with value number 1. So we don't have to worry about it. Now at this value number 2, let's say, let me just clean this up a bit. Now we are making a new decision tree, a new decision path, where we have 2. Once again, we go to the next element, that is once again 2. After doing this, we go to the next element, that is 3. So now this sum in total becomes 7. So 7 is greater than 5. If 7 is greater than 5, going down this path 2 does not make sense. So we are going to ignore that. Ignoring this, we are going to be going with 3. So we are at this juncture, and we found that current sum is 5, which means this is one more potential answer that we will have to record. So let's mark this one. Okay, marking this, we are not done yet, because we may still find another results, we don't know. So we go to this next element, 2 to 4, but this also leads to result number 6, which means we calculated all the possibility at this current 2 as being the very first element where we are calculating. Now the thing is, next element is also value number 2, and we can see that with previous element 2 we already calculated all the possibilities. So if we had a target value, let's say instead of over here instead of 5, if we had a target value 4, we would have a potential value 2 that is being generated by this 2 already. So we don't have to do anything over here. And also, if we try to go down this path, let's say that we ignore my advice for now, and we say that currently we took care of this one, we took care of this 2, this 2 is still valid and legitimate. So now we have this value number 2. Once again we go down to the path, so we find value number 3 as the next potential match, and this matches. So should I add it to the answer? No. Why should I add it? Because I already calculated this one. So what I'm suggesting is that once we have the sorted list, we simply check that for any particular element that we are trying to iterate over in the recursive manner using our backtrack function and recursive function, we first check that whether if it is the same element as the previous element. If that is the case, we already calculated all the possibilities and added to our answer, so we can simply ignore that. So now we are all going to be ignoring this 3 as well. Now we are left with this element number 3. So let's try to make possibilities with this 3, and we are just going in one direction. We are not going in the opposite direction because we calculated all the possibilities. So with this 3, the only possibility we have is to add value number 4. The sum is going to be 7, so greater than 4, which means this leads to no result. So we already calculated all the possibility as 3 as well. Now next is the only element 4. Once again, if we calculate the possibility, there is only going to be just element number 4, which is not 5, so we cannot put it in the answer. After this, we are done with all the elements in our input, and this is the answer we need to return. So now let's do a quick recap. What we did, we calculated that what was the backtracking function, and we also calculated that what is going to be a recursive approach. For a recursive approach, we need two items. We need a base case, and we need a recursive call or recursive function. We know that what is going to be our backtracking logic, that at every possibility, the moment we either reach to the target value is equal to 5 or target being greater than 5, in either case we are if it is 5, we are going to be adding it to the answer. If it is greater than 5, then we are going to be going to the very previous element that we were iterating over and remove that from our current list and follow along with the remaining possibilities. That is option number 1. For our recursive, the logic is quite straightforward. Base case is going to be that the total sum of the current elements that we are iterating over, it's either 5 or greater than 5. If it is equal to 5, we add it to the answer. If it is greater than 5, then we can simply just move forward or jump to the next element. And for the recursive function, we are simply going to go in a normal fashion by adding the current value and removing the current value from the given input array, and just making a recursive call by adding a new value that is next inside our given array. So if we see the coding solution, it would make much more sense, and this is, in my opinion, a very beautiful solution. So I hope you understood what I was trying to explain. Now let's quickly see the coding solution for this one. So here is the coding solution. First of all, we are generating our result where we are going to be storing the list of array list. Then we are sorting the given candidates array. Plus we are going to have our backtrack recursive method where we are going to be doing backtracking and also making recursive calls. And so now let's understand our backtrack method. So first we are passing in the result list that we just created. We are also maintaining a current list. We are also maintaining the candidates array that we are iterating over. On top of it, we have provided our target and we have provided our start values. Okay. Very first thing we are doing is checking that if the given target is equal to 0, then we are going to be adding the current list inside our result, and we are simply going to do a return from our current recursive call. If that is not the case, we will run our for loop where we are simply going to iterate over all the values that are currently present inside the candidate. Very first thing we are doing is skipping the duplicates. So we are checking that if the current candidate is same as the previous candidate, we can simply ignore that value. Next, we are also doing an early termination if the sum becomes negative, because at every given moment, the moment we see a new ith value, we subtract that ith value from the given current target element, and the moment we realize that this is going into the negative, we are simply doing a break operation. Now if that is not the case, we add the current value to our current array list that we are maintaining. Then we once again make a recursive call with the current value, which contains one more value right now, and we provide the target minus candidates I, because we are subtracting the value from the target that we need to achieve, and we update it with the next element inside our for loop, and that's it. Now once we get a result back from our backtrack, we simply remove the very last element, and we once again do the same operation for other possibilities that we are yet to calculate. So this approach should work. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions, which is pretty good. So once again, I would be posting this solution in our GitHub repository, so you can go and check it out from there. Thank you. Hello friends, I am a cloud solutions architect at Microsoft who like making these videos, and today we are going to solve a LeetCode problem called generate parenthesis. Now if we see some of the popular companies who have already asked this question, there are companies like Amazon, Facebook, Microsoft, Apple, Bloomberg, Uber, Lyft, Google, ByteDance, Spotify, and Nvidia. So that's why I am paying my utmost attention. I hope you also enjoy the video. Okay, so this is a LeetCode medium problem and also very well like problem on LeetCode. Basically, we are given an input number n, and now we need to generate n pairs of parentheses. So basically, we need to write a function that generates all the possible combinations of well-formed parentheses. Now these round parentheses, I think they are called well-formed parentheses. Now we can try to understand these two examples, but I'm actually going to take it one step further, and I'm going to show you 4 different examples to understand that what this problem is asking us to do. Okay, now in this first example, we are basically given n is equal to 1 pair, which means we need to make one possible pair and all the combinations of this well-formed parentheses. So obviously the answer is going to be quite simple. We simply need to return like just one possible pair that we can make out of this one. Now suppose n is equal to 2. So now for n is equal to 2, we have the choice to take like 2 of these and 2 of these. Right, we need to take 4 values. So basically the number of possibilities we can make is that we can actually make a parenthesis that looks like this, and we can also make a parenthesis that looks like this. These are the only 2 possibilities we can have, and this is what we need to return as the answer. Now things becomes a little bit interesting when we reach to n is equal to 3. So when we get to the point where n is equal to 3, the possibilities we can make is, so these are the 5 possible pairs we can make when n is equal to 3. Now notice that over here for every single piece we are using like 3 opening brackets and we are also using 3 closing brackets, but we are just putting them in different pairs so that they generate like the well-formed parentheses. Same way, if we try to do it with n is equal to 4, the answer is going to be pretty huge. So let me just draw it over here. So these are all the possible pairs we can make when n is equal to 4, and basically we are using 4 opening brackets and 4 closing brackets and arranging them in different sizes. So this is a very interesting problem. Now let's see that what are going to be the different approaches to solve this problem. So now the first approach that comes to our mind is a brute force approach. In the brute force approach, what we can do is, suppose we are given n is equal to 2, right? If we are given n is equal to 2, there is one thing guaranteed. We need to have 4 characters inside every single block of our answer. Why 4 characters? Because we are generating 2 pairs of parentheses. So 2 pairs of parentheses is basically going to be 4 characters at least, right? So what we can do is, now we have 2 options to choose from. Either we can choose an opening parenthesis or we can choose a closing parenthesis. So what we are going to do is, basically we can take every single possible pair that we can make of size 4 using these 2 characters, and only the valid pairs we put them in the answer. So suppose we are given n is equal to 2, what are the different pairs we can make? Let me make just a few pairs. So these are just some of the few examples that we can make for 4 characters using like this opening and closing parentheses for n is equal to 2. And over here we only need to find the legitimate pair. So okay, we can find one legitimate pair and we can find another legitimate pair, and I think this is going to be the answer that we need to return. So we will put these two in the answer and then just return them. But if you see, this brute force approach is extremely inefficient. If we see like time complexity, the time complexity goes sometimes into like 2 to the power of 2n something multiplied by n, just to check that whether the pair is valid or not, and that is disastrous. So no one is going to accept that. So we will have to find a way to do something better. So what we are going to do is, we are going to do things smartly. How we are going to do things smartly? First, let's define our purpose. Our purpose is to generate 2 pairs of opening and 2 pairs of closing brackets, and they has to be well informed or valid. Now we need like 2 opening brackets, so that is a given fact. We need 2 closing brackets, that is also a given fact. Now there are some properties that we can use at our advantage, taking consideration the definition of being valid. Now what is the definition of being valid? So basically, if we are given n is equal to 2, there has to be 2 opening parentheses and 2 closing parentheses. So that is one definition. Second definition for being valid is that we can only put a closing parentheses if there exists an opening parentheses before that. Again, I'm repeating myself. We can only put a closing parenthesis if there exists a closing parenthesis before that. We cannot start our answer with a closing parenthesis, because that wouldn't be valid. Third thing that we need to consider is that we can only have that many number of open parentheses that is equal to the number of n. Now you are saying that why am I repeating myself? Because this is going to be the very important property that we are going to use. So now once we know all of these things, let's try to make some smart decisions on how we can actually generate the answer for valid parentheses. Basically, we are given n is equal to 2 over here, right? Now we have option to choose like 2 opening parentheses and 2 closing parentheses. So okay, now what we are going to do is, for our answer generation, always we will have to start with an opening parentheses, right? Now we created the opening parentheses that starts with this one. Now we are going to keep track of few values. First value we are going to keep track of is the number of opening parentheses, right? So number of opening parentheses that we have used so far is 1. And what is the maximum we can use? Maximum we can use is 2, because that is the value of n. We are also going to keep track of the number of opening parentheses. We already know that is 1, right? We are also going to keep track of number of closing parentheses, and so far we haven't used any closing parentheses, so that this value is 0. And we can only add a closing parenthesis if the number of opening parentheses is greater than the number of closing parentheses, because we already proved that over here. Now using this logic, let's see that what is the sequence we can make. Okay, so first we start with this value. When we start with this value, number of opening parentheses is 1, number of closing parentheses is 0. Now over here we have 2 options, and those 2 options are, we can either add one more opening parentheses or we can add a closing parentheses. So let's see options in both of the cases. The number of opening parentheses is going to be 2, and we can have this value to be 2 because we are given n is equal to 2. And in this case, the number of closing parentheses is still going to be 0, because we have only used 2 open parentheses over here. Now in this case, the answer is going to be a little bit different, because the number of opening parentheses is going to be 1 and number of closing parentheses is also going to be 1, and this is also valid. Why? Because the number of closing parentheses can be 1 because we already had 1 open parentheses. So far both of the cases are legitimate. Now again, at this position we also have 2 more choices. So over here we have the one choice to open and we have one choice to close. Now let's see both the options. If we try to go one choice to open, what will happen is number of opening bracket is going to be 3, but that is not valid. Why? Because we are given n is equal to 2 explicitly. So in this case we cannot go down this path. So if we cannot go down this path, we will actually backtrack and come back to this position. Now from this position we can only go towards the path of closing. So if we go towards the path of closing, so far the number of open brackets we had is 2 and the number of closed bracket we had is 1. So that is still valid, that is still legitimate. Now again from this position we still have two options. We can either open or we can close. If we try to open, we cannot do that because number of open is going to be 3, so we are not going to go down this path. If we go down this path, basically the number of open bracket is going to be 2, number of closed bracket is going to be 2 as well. And this is the exact condition we need, because we are given n is equal to 2, so which means that there has to be 2 open brackets and 2 closed brackets. So we can put two conditions, whether we can put like the combination of open plus close is going to be 4, that is going to be the double of what is n, or we can have like O is equal to 2 and C is equal to 2, both of them equal to 2. So this is also good. So now we have reached this condition, which means that whatever the path we actually make can make ourselves into the answer. So what is the path we took? So first we started with taking the opening bracket, then again opening bracket, then again closing bracket, and then again closing bracket. So let's put this value in the answer, right? So we are going to create a new variable answer over here, and over here let's put one entry that okay, 2 open, 2 close, that is good. Now let's start following the other path. I'm going to clean this up a bit so it does not become any more distraction. So now in this case, okay, currently we have one open bracket, one close bracket. Now again we have two possibilities. So first possibility is we can open one more bracket or we can close one more bracket. Now let's analyze both the possibilities. If we try to open one more bracket, basically the number of open brackets we are going to have is 2. Let me clean this up a bit more. And over here number of closed bracket we had so far is still 1. So okay, this is valid, we can put this one. Now if we try to put one more closed bracket, the number of open bracket we have so far is only going to be 1, but number of closed bracket is going to be 2, which is a big no. Why? Because we cannot have more closed bracket than the number of brackets we have opened, because that would defy the possibility of having a legitimate scenario. So we cannot go down this path, so we won't. And now again we have two choices at this position. We can open one or we can close one. If we open one, then the number of open is going to be 3. That is not valid, that is not good. So we are not going to do anything with this one, and we will not go down this path. If we go down this path, then over here number of open brackets we have so far is 2 and number of closed bracket we have so far is also 2, which is also the legitimate scenario. So which means that this path is also going to be a path that we can add to our answer. And let's see. Okay, so currently we have, okay, we have one open bracket, one closed bracket, we also have one open bracket and one closed bracket, and that's it. Now initially, remember, we only started with this one opening bracket and then we had two possibilities, and we actually exhausted both the possibilities, so we cannot go down further anymore. Now because we cannot go down further anymore, we can conclude that whatever the values we find so far, this is the complete answer, and we can return this as the answer. And basically this is the whole crux of the finding the optimal solution. Now you must be asking that hey, what we actually did was we did something very important. First we identify, okay, the one value, then we had the final case. So final case was that whenever the number of opening is equal to n and number of closing brackets is also equal to n, this is our final case. And then at every single position we had two options to either choose an opening bracket and closing bracket and keep on repeating the same process until we reach to the end, and we had some parameters in mind. So if you see, we are actually using dynamic programming at its finest, because at any single previously computed value, that is being used to calculate that which path we need to take and whether we can take that path or not. So we are basically using dynamic programming plus backtracking to solve this problem, and this is going to be like an amazing way to explain this problem. Logically think that in the brute force, what a disastrous result we were having, and we actually brought it down to such like beautiful answer, and then we are just presenting it. So this is the whole power of using any like computer language. So before we start implementing the generate parentheses method, first we are going to create our backtrack method. That is going to be our helper method that we are going to use recursively. Now for the backtrack method, it is not going to return anything, but it is going to add all the values towards the answer. And inside the method, we are actually going to create a list of lists that is going to store the answer. We are also going to have a string builder to keep track of the current values we have, and the number of opening and number of closing brackets, and also the maximum number of values we can generate. Okay, so now first let's create the acceptable scenario. So if basically the current length is actually going to be maximum times 2, which means that we have reached to our answer and we can add it to our answer. So this is the legitimate scenario. Now let's see, say for an example, we find out that we have not reached the answer. Then what could be the possibility? Well, first possibility could be the number of open brackets that could be less than the number of maximum brackets that is allowed. If that is the case, basically for the current string builder, we can actually append an opening bracket. So let's do that. And after adding the opening bracket, basically we will have to call the backtrack method again with a reduced value of one open bracket. So let's do that. So in the backtrack method, we are going to call the answer, and we are also going to call the current string builder list we have. But for the open, we are actually going to add one value, and for the number of close brackets, we are going to keep it as it is. The max is also not going to be changed, and that is awesome. Now there is also one more important thing we will have to do every single time we make a backtrack call, and that is to delete one character that is located at the current length -1, because it is going to add an extra character. So let's do that. Okay, now same way, say for an example, if the number of closed brackets and they are less than the number of open brackets, if that is the case, basically we can also add one closed bracket to our self as well. So let's do that, and we are also going to call the backtrack method, and everything else is going to remain the same. And basically this whole logic sums up our backtrack method. Now all we need to do is, from our main method, we simply need to create a list of lists called answer. So let's do that. And then we are going to call our backtrack method. Now inside the backtrack method, we are going to provide the value of answer. We are also going to provide a new instance of a string builder. Going to provide the number of opening brackets that we have used so far is 0. Number of closing brackets is also 0. And the maximum number of opening and closing bracket we can have is going to be the value of n. And after getting the answer from the backtrack method, we can simply return the answer to be return the answer that we got. And basically that's it. Yeah, let's try to run the code. Okay, seems like our solution is working as expected. Let's try to submit the code. If we submit the code, our solution beats a lot of other solutions. It is really good in terms of time complexity, and it is also really efficient in terms of space complexity as well. So yeah, I'm going to be very satisfied with the approach, and now I would be posting this solution in the comments, so you can check it out from there. Thank you.
Hello friends, hope you are having a fantastic day today. So in this video, we are going to do a very popular LeetCode problem that is going to be pretty nostalgic for a lot of people. So without any delay, let's get started. The title of this problem is called letter combination of a phone number, and now many of the iPhone users won't know it, but in the past phone actually did used to look like this, where if you have to type any messages, you will need to do it according to the keys that are present over here with the corresponding numbers, and people were so good that they were able to do it without even looking at it. But anyways, now coming back to the question, this is a LeetCode medium problem and also an extremely well-liked problem on LeetCode. Also has been asked at tons of popular companies. So let's see that what does the problem statement ask us to do. Basically, we are given a string containing digits from 2 to 9, because notice that in this problem, we are only given the characters from A to Z present between the letters 2 to 9. Now, inclusive, now we need to return all the possible letter combinations based on the given digit numbers, and that it can be represented. For our convenience, we can return them in any order. So let's try to understand this with a couple of examples. Suppose we are given as an input just character number 4.
So how many characters does this character number 4 can represent? Well, only 3 characters. So if we have to return this, the answer is going to be G, H and I as the answer that we need to return. But let's assume that instead of that, we are given the input as like 4 and 6. Then what should be the answer? So we know that 4 can represent G, H and I, and 6 can represent M, N and O. So the answer is going to be the combination of both of this GHI and MNO. So the answer would look something like, where you can see that currently we have 9 entries and they are combination of all the characters from these two entities, and that's what we need to return. So this is the whole problem statement. So let's try to see that what is the approach we can take to solve this problem. Now, number one thing is that currently we are only given characters between 2 to 9 as an input and nothing else. So first thing we need to do is that we will have to create a mapping so that based on any given input location, we can actually identify that if the character 2 is given, we know that it can only have the possibility of storing ABC. Same way, if character number 9 is given, then it only has the possibility to store 4 characters W, X, Y and Z. And same way we can store this in any such fashion so that this lookup needs to happen in big O of one time. So we actually have two options to do that. Number one option is that we can actually create a hash map, and inside the hash map we can store all the entities, and based on the key we can mark as the digits, and their subsequent values we can mark all of the entries. So that is option number one. This will yield in big O of one time complexity whenever we have to do the lookup. Second option is, since we know for sure that we are only dealing with characters between 2 to 9, nothing more, we can also create an array, and inside the array, based on the index positions, we can store the values. So let's assume that because in the array we have values like 0, 1 and then 2 and all, or so on and so forth. So for 0 and 1 we can store as an empty strings, because anyways they are not going to be part of our inputs, and starting from position number 2 we can start storing values as A, B, C and stuff like that. Now this is only for our convenience purposes, so that we can quickly look up what element we are trying to find. Now this is the pre-work that needs to be done in the solution so that we can do it in the efficient manner. Now let's see that what is going to be the optimal approach to solve this problem. Suppose as an input we are given the characters 2 and 3 that we need to return. Now we know that 2 is represented by ABC and 3 has been represented by DEF. That we actually take this given input 2 and 3, then we break this input based on all the digits it currently has. So first we get the digit 2. For digit 2, whatever the characters that it can represent, we create 3 decisions trees based on that. So currently it can represent A, B and C. So we create 3 separate decisions tree. And now, since this is not the answer, because we need to return the combination or the potential combinations that can be there. So this is just a part of the answer that we have created so far. But now we will have to complete the combination portion. So in order to do that, the number one thing we will need to do is to keep track that how many number of characters are currently present, or how many number of digits are present and how many are pending. So now 3 is pending. So we will append 3 with each of these decisions trees, and we know that 3 is currently represented by these 3 values. So once again, for each one of them, we are going to have 3 separate decisions tree being made. Notice that currently at this very first location 2, we only had one entry per character inside our representation. But the thing is, in the input we were given 2, 3, 23, which means we were dealing with 2 character letter. But in the problem, we are only at half of the step, where we only have just 2, which means after creating this possibility, we still have to wait to add the values to the answer until we find this path where now the index position matches the total number of inputs that we are given. The moment this condition matches, we will need to add it to our answer list. So because over here we only had one characters, but now we had 2 characters, and even in the input we were dealing with 2 characters, we are going to add DA or AD in the answer. Same way AE is going to be part of the answer. Same way AF is going to be part of the answer. And the good thing about this is because this is same operation being done multiple times, so we can actually keep on doing this. The moment we find out that this is one of the potential pair that we have already added to our answer, we can actually backtrack to see if A still has any more values that it needs to add to the answer. And yes, AE still needs to be added. So we will add AE. Once again, we will backtrack to A, and once again this AF needs to be added. So we will do that. Once again, we would backtrack to 2. Now we have completed all the path with A. So we will repeat the same process with B. And this is the whole answer we need to return. Now I know what I just explained might have confused you a bit. So that's why when we do go into the coding section, I will explain the whole thing in much more clarity. But this is the whole approach. Basically, we are simply using recursion and backtracking to solve this problem, because repeatedly we are doing the same operation, and we know that for this we need to have an terminating case. So terminating case would be that the moment we identify that one path or one combination contains the same number of characters as the number of input that is given or the index values, then we need to add it to the answer and once again do the backtrack, keep on repeating the same process until we have exhausted all the possibility, and whatever the answer we found, we need to return that. Okay, so what is going to be the time and space complexity in this case? The time complexity is only going to be the number of potential combinations that can be made, which means the number of characters that are given. So let's assume that this currently has 3 times 3, 6 characters. So whatever the value is, so we need to do square of the number of given input for every single digit. So in total, it is going to be the number of combinations that are currently present. That is going to be the time complexity. For the space complexity, because we will have to create another array that contains all the mapping from the characters 2 to 9, we will have to store that, but that is going to be limited in scope. So instead of calling this as big O of n, we can actually treat it as big O of 1, because the space complexity is not going to change. So now let's see the coding solution. Okay, so first of all, we are going to initialize our string array, where we are going to mark first couple of entries as blank, and then we are going to mark all the values. So this is going to allow us to iterate over all the digits to the letters. And then let's start our code actually for the problem statement for this method letter combination, where we need to return a list of strings as the answer. So first we are going to initialize a combination string that we are going to return as the answer, and this is going to be the blank array list so far. Now first we are going to check for an edge case, that if the given number of digits is equal to null or digit.length is equal to 0, then we simply need to return combinations. If that is not the case, we are going to call our backtrack method, and we are number one thing, we are passing this list that we have created. We are also passing the input digits that we have received. We are passing an empty string that is going to be considered as the current combination that we have so far, and we are passing in 0 as the current index values that we have processed so far. Okay, now let's see this backtrack method. How does it work? So number one thing we are checking is that if this given current index location, if that is equal to the digit length, which means we have an answer that we need to add to our current combination. So we are going to add all the answer that we have found in the current combination to our combinations array list that we have created. If that is not the case, we are first of all going to differentiate the letters for every single index position. So let's say in the input we are given value number 2, then we would have ABC as the letters passed on, and then we are going to run a for loop across every single letter. But now this time we are recursively going to call back the method backtrack. We are passing in the same combination, same digits, but for the current combination, we have added the current combination plus the current letter we are working on. On top of it, we have also updated the number of increase value, index value. So if in the previous iteration, if we would have passed in value number 2, in the next iteration, we would have passed in value number 3. And that's how we will be able to start storing all the combinations in the current combination array string that we have created. And this is it. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions, which is awesome. By the way, you can always find this coding solution in the GitHub repository we have, and the link is in the description, so you can check it out from there. Thank you. So the LeetCode problem we are going to solve now is called palindrome partitioning. We can see that this one is a medium problem, but in my opinion, this should have been a hard problem. We can see that this is a very well-like problem. Now let's understand that what is being asked us to do. We are given a string S and we need to partition this string S such that every single substring of that particular partition becomes a palindrome, and we need to return all possible palindrome partitionings of S. So it sounds a little bit awkward, but let's try to understand this with an example. First, let's understand that suppose we are given a string S such that the values are A, B, C. So we can see that in this case, if we have to partition string, there are a bunch of different options. We can have a partition that is completely like this, or we can do a partition like A, B, and C, or we can do a partition like A and B, C, something like this one, right? There are a bunch of different ways for us to partition any given string. But the thing is, in this case, we need to find partitions such that every single partition becomes a palindrome. Now we all know that what is the definition of a palindrome. Suppose we are given a value like this ABA. In this case, this ABA is a complete palindrome. Why? Because if we write it from left to right or right to left, in both the cases, the answer is just going to be ABA. So same way, this let's say if this is the input we are given, and if we have to partition it in such a manner that every single substring of that partition becomes a palindrome, we only have one possibility. That possibility is if we partition it by using just individual characters, because an individual character in itself is a palindrome. Because let's say if we only have one value, you can read it from left to right or right to left. In both the cases, we are going to be left with the same value. So this is the only answer we need to return in this case. But let's say that we may have been given some other options. Let's say that our given string S is equal to values such as A, then A and B. Okay. Let's say our given string S is equal to values A and B. So now in this case, we will have two options in order to generate the partition. First partition is going to be quite straightforward, that is taking on individual characters because they are palindrome and their own, and combination of these characters actually form in such a manner that every single character is a palindrome in itself. But we can make one more distinction or one more answer in this case, where if we create a partition of these two values A as one partition and we create another partition of this individual character B, then also this becomes a valid partition of the substring such that every single portion of the partition actually forms a palindrome, because this A is a palindrome and this B is a palindrome in itself. So this is what the problem statement is actually asking us to solve. Now let's try to understand some logic on how we can actually solve this problem. Well, if we just have to solve it using pen and paper, what is going to be the first logic you are going to apply? Well, the very first logic is that we will start iterating over this given string character by character, comparing every single character with the previous characters that we have been able to find so far, to determine that whether using the combination of previous characters are we able to generate palindrome or not. If we are able to generate a palindrome, we would mark it as one of the partition and then we will keep on moving forward. So let's try to understand the approach I'm suggesting. Let's say over here we start iterating over at this very first element A. Now for this very first element A, the moment we come to this element A, we have two choices. One choice is that A in itself could be a palindrome. So we mark A as a palindrome, and same way there could be another possibility that we may find some value where this A could be potentially part of some future palindrome that we are yet to discover. So let's leave this possibility open for us for the moment. Okay. Now, if we decide to create a partition based on A, then once again, we have the option to move forward with a single A or the next element. So let's say that once again, we decide to move in with a single A and create another partition, which this is the first partition and this is the second partition. Okay. And once again, we move to the another value. And for this next value, we encounter value B. So once again, we create a partition in its own. Now the thing is, when we reach to this B, we realize that now we have reached to the end of our array. So far, all the values we find inside or all the partitions we did for our given string s, all of these values are palindromes, because let's say that in order to determine that whether any particular string is a palindrome or not, we are actually going to create a method that checks that if the given string is a valid palindrome or not. Okay, and this string is quite straightforward. They are the values of itself, so we know that all of these values are correct palindromes. And we are also storing some current array list where we are keeping track of all the current values that we are iterating over one by one. So we realize that this is the correct sequence of the partition that generates a palindrome. So we are going to mark this option inside as part of our answer. After marking this, we are not done yet, because once again I mentioned that there could be some potential ways or some potential other paths that we are able to generate, which could lead us to more palindromes that we are yet to discover. So once again, let's try to apply that same logic in this case. So now once again we already explored this path. Okay, now what we are going to do is we will do a backtrack operation once again to the very first character to make sure that maybe we did not miss out some palindromes that we could have found. So let's say that we, instead of just creating a single value partition, from this single value we actually decide to do a partition of two values. So creating a partition of two values would give us value a. Once again we check that if is this a valid palindrome or not, and yes, this is a valid palindrome. So we are good to continue to the next element. For some reason, if we identified that this was not a correct palindrome, let's say for some reason that this value given is x, so then this ax is not a correct palindrome. If this is not a correct palindrome, then it does not make sense for us to continue down this path of partitioning. So then we would choose a different path where after this ax we would actually include b in our decision making as well, but there is no need to do that. So let's leave it as it is right now. So after leaving it as it is, okay, so we created another partition at this moment aa. The answer is valid, legitimate, so we are keeping it as it is. After keeping this as it is, now we decide to go to make another partition, that is this value b. So once again we create a single partition of just one value b. This is also a palindrome, and with this b we reach to the end of our list. So after reaching to the end of our list, we are also going to be marking this sequence that we found as part of the answer as well. Now let's try to clean this up a bit, and now once again we are yet to explore more possibilities that we haven't found, so we will also try to do this one. Now for the more, initially we took down a possibility where we are only partitioning the string based on just one value. Then we partitioned the string by using values a, and then also it worked out. Now we are going to partition the string based on considering all three values. So let's say that we just create a partition that is a and b. Just because this is definitely not a palindrome, plus we reach to the end of our list. So now we are done with our search with starting all the possibilities from this current value a. Now we are yet to identify more possible palindromes that we are yet to identify. So let's say that in the very first beginning when we made this partition, now we will continue down this path, but previously we went down this path, that was this answer over here. Now we will try to choose a different path, and in this different path what we are going to do is, with this a, now we are going to pass the baton on to the next element, and now we will say that, hey, next element, if you want to do or try some partitions, let's check those. So once again from this a we can create another partition like ab, but definitely this partition is not a palindrome. So if this is not a palindrome, then it does not make sense for us to continue down this path, and anyways we are running out of elements in this case. But let's say if we had some more elements over here, let's say some more element like say c. So do you think it would make sense for us to create a partition such that a, b and next element to c check like this? No, because we already know that this is not a palindromic substring. So why even bother checking? So then in that case our logical step would be to include c as part of one of the possibilities as well. But once again this is also not palindrome, so now we can be done with this. So this is the simplest approach we can take to solve this problem. Now we all know that what we did, we use the backtracking option to basically go through all the possibilities that we can in order to generate or find sufficient answer. Now let's try to understand that what has to be the logic of our backtracking function. This is going to be a simple function that takes the current partition that we are dealing with, and based on the partition from the input string, it is going to have a starting index for the next partition that we are going to check with. And with the starting index of the next value, we should be able to understand that are we at the end of our string or not, and whether we can conclude the current partition to be over or not. On top of it, with every single value, we are going to check for any particular substring that we are generating, that whether that is a palindrome or not. And in order to do that, in order to accomplish all of this, we will actually use recursion. Now for recursion, we know that we have two items that we need. First one is a base case and second one is a recursive function. Base case is quite straightforward, that if I previously mentioned that we are going to have a variable called start to keep track of the next index. That would be the starting point of the next sequence of palindromes. Let's say that we created a subsequence like this, AA as one of the palindrome, then start index would be living over here with value number 2, as that is the logical starting position. So we are going to check that if for the current list we come to a place where the starting index is the length of the given string, then we are going to be marking that current index as part of the answer and returning or coming back through our recursion. So we identified our base case. For the recursive function, we will have to do two things. First thing is that for every single new partition we make, we will have to check that whether this one is a valid palindrome or not. If let's say that that is a valid palindrome, then it would make sense for us to call the recursive function once again with the next value in line and creating the current partition as it is. Now I know it sounds confusing, but if you just understand that or try to walk over the solution that I presented, then it would make absolutely beautiful sense to you that what I'm suggesting. And on top of it, for the recursive function, we are also going to be updating the current index value that we are iterating over. Let's say that we iterated over AA, so then we will have a recursive function starting with value number B, and once again we will try to repeat the same process. Combination of all of this should give us the answer, but thing is, this is not just enough. Once we receive a call back, and we will have to check for other possibilities, where first we check for the possibility of A only, then we may have to check for the possibility of AA. So in order to do that, we will have to do a backtrack, and for the backtrack, the simplest thing is to remove the very last element we added inside our current array or current array list, and once again repeat the same operation. So basically combination of backtracking and recursion is the way to move forward in this case. Now let's try to calculate the time and space complexity. Well, time complexity is difficult and tricky to calculate in this case, because we don't know that how many number of potential partitions we can make. So at the end of the day, this is simply a decision making algorithm, and in the decision making algorithm, at every given step, let's say that we created a partition like this A. Now we will have to check whether to include this A or not to include this A as part of the partition. So at every given step, we are checking for or to whether to make that decision or not to make that decision. So basically we have 2 to the power of n possibilities, where n is the number of characters given, and for every single character we will have to repeat the same operation. So it's going to be n multiplied by 2 to the power of n possibility, and that's why this is a very expensive operation. And if you go through the LeetCode problem, we are only given like up to from 1 to 16 as part of the range of n for the length of the string, because they also realize that they don't want to put much load on the LeetCode servers. So now let's try to quickly see the coding solution for this one. Okay, so the very first thing we are doing is that we are generating a new result array list that is going to store different array list inside it to store our answers. Then we are going to have our backtrack method, where we are passing in first of all the result array list we created. Then we are also passing in the current list we are iterating over, passing in the given string that we are given as the input, and we are passing in the starting value of the next pointer that we should consider for the partitioning. This is the starting pointer that I just mentioned. Okay, now first of all, let's see, in our recursive function we are going to have our base case, where we are first checking that if the starting value is the length of the given string, which means we are actually reached to the end of the string. So we can add the current result we are iterating over inside our result array list, and we can simply do a return call from the iterative stack. And now let's check our recursive case or recursive function. So for that, we are basically iterating over from the starting index till the end of this list, and we are updating the value. And here I mentioned starting and ending pointer. This is just simply so that we can check that the given palindrome or the given sequence of element partition we are iterating over, if that is a substring or not, we can simply make that call. So first thing we are going to check is that if the given current substring, is it a palindrome or not. For that, we have created is palindrome method, where we are doing nothing but we are simply iterating over from both ends, like starting pointer and ending pointer. If at any given moment we identify that there is a mismatch, we simply return false. If that is not the case and we complete the whole iteration, then we can simply return true, saying that this current substring is a palindrome. Okay. After determining that the current set of partition is a palindrome, we are going to add that substring to our current list that we are maintaining. And once again, we are going to recursively make call with the same values, except the next index position that we will have to iterate over, and that is going to be our end +1. You can also define this end instead of end to be I as well. I just put in end for it so that it becomes better readable for our is palindrome method. And once we get a result back from our backtrack method, we are simply eliminating the last value we inserted inside our current list, because we still have to explore more possibilities. And this is our backtrack function basically. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to 98% of all the other solutions, which is exceptionally good. Once again, the solution of this code is presented on our GitHub repository, so you can go and check it out from there. Thank you.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do word search lead code problem, and if we see the number of companies where I want to work at who have already asked this question, there are companies like Amazon, Twitter, Microsoft, Uber, Bloomberg, Facebook, TikTok, Snapchat, Google, Apple, Samsung, Roblox, Goldman Sachs, ByteDance, and eBay. So these are really popular companies, and this problem is really popular because it has very real life applications. We have all played games like crosswords and Wordle on our phones and on the newspapers and different kinds of stuff. So that is where this problem is associated with, and we are going to see that how to solve this one. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given an m cross n grid of characters called board, and we are also given a string called word. Now we need to see that if this word can be created based on whatever the number of characters we are given on this board, and if it does, we need to return true, else we need to return false. Also, we are given a note that the word can be constructed from letters sequentially adjacent cells, where adjacent cells are either horizontally or vertically neighboring. And we are also told that same letter cell may not be used more than once in order to create that word. So let's try to understand this with an example. Over here we are given this big board, and on this big board we are told that we need to find the word A, B, C, C, E, D. So if we see over here on these marked values, so this starts with the word A, the neighboring word is B, the neighboring word is C. Again, we are told that we can horizontally or vertically see the words. So if we go vertically downwards, we see another C, and then we find another E, and at the end we find D, which is also adjacent to E, which is this letter, and this is basically part of this given board. So in this case we can return true.
Now suppose if this word if we were not able to construct this word, we would not return true and we would return false. So let's see that what would be the optimal approach to solve this problem. Well, we have actually solved similar problems like this in the past using DFS and backtracking, and this is what we are going to do for this problem as well. Let me quickly show you how. Okay, so suppose this is the custom example we are given, and we need to find the word spider to see that whether it exists on this given board or not. And the idea is actually quite simple. What we are going to do is, first of all, we are going to take the first character inside this word, which is S, and we are going to iterate over this matrix until we find this first character. The moment we find the first character from whatever the place is, then we will keep on trying to find the next letter, the next words inside this word, to see if it exists in the neighboring node or the neighboring cell of the board inside this given matrix. And if somehow we are able to reach to the end of this word, we can return true. If we don't reach the end of the word and we actually reach the end of the matrix, we can return false. So the idea is actually quite simple, and there are just few tweaks we will have to use in between. So first we will start iterating over this matrix, trying to find this word number S. Now this is not S, this is not S. Over here we find the first value as S. So because this is the first value as S, now we will have to try to see that whether this P exists or not in the neighboring node of this S. We can clearly see that P exists. But before doing that, what we are going to do is we are actually going to mark this node as visited. So one way to do is to use some visited hash set and store all the values, but that is just causing strain on and to have an extra memory usage. Rather than doing that, we are going to actually modify this input and we are going to mark it something like hash or something, which is an invalid value and it can never be there. So which means at any point we encounter that this value is hash, we don't need to go back to that place. Now we will start iterating over the neighbors of this S. So neighbors of S can be these three places. If we try to look at these three places and we are looking for the alphabet P, so P is present over here, which means that so far we have found S and P. Now we will update our value to I, and we will try to look for I in this P's neighbor. Also we will mark this node P as like hash, so we don't come back to this place again. Now this P has only two neighbors because this neighbor S has already been visited because its value is hash, so we can't do anything about it. Now we are looking for this letter I, and we find the letter I over here, which means again we will mark this as hash. We will update the value of word we are looking for. The word we are looking for now is D. We'll try to find the neighbors of I, and in the neighbors of I, okay, we don't find anything over here. This is not D, and this has already been visited, which is hash, which means that there is no neighbor of I that contains this value D, which means that now we haven't found the word so far, and we still have matrix to go to that we haven't visited so far, which means that now we will backtrack from this I to the position we were originally at, which means that from this I we came from P, from this to this P we actually came from S, and now we can say that okay, even in this S it does not lead to us to find this word, and then we will again proceed with our search. So again we are trying to find this letter S again and not the D, because we did not find anything in the route, which means that now okay, this P is not S, this I is not S, this T is not S. So we are good so far. Now at this position we find a letter S, which means that okay, this S has been found. Now in the neighbor of this particular cell we will have to find the letter P, and we are going to mark this S as hash as a way to identify that this has been visited. Now what are the neighbors of S? These four are neighbors of S, and the one value we can find where the P exists is this one. So again we will repeat the same process. We will mark this as a hash. We'll try to find the word I we will find over here. So again we will mark this as a hash, and we will try to find D in the neighbor of this I. So we find D over here. So again we will mark this as hash. We will go update the word we are looking for, and now we will try to search for E inside these neighbors, and we can find it over here. Again mark this and then try to find this R. So R we actually find in the neighbor of this one, and this is the correct R. which means that now we are able to reach to the end of this word list, and we can return true in this case, saying that okay, this actually exists inside this given board, and we will be good. So this solution works perfectly fine. Let's see the time and space complexity with this one. So for the time complexity, actually the time complexity is a little bit tricky to find. Why? Because the time complexity is actually big O of n, which is the number of cells. So for every single cell we will have to iterate at least once. So n is given, but then we will have to repeat the same process for 3 times to the length of L in the worst case scenario. Why 3 times to the length of L? Because notice that at any single position, suppose we were at this position number D, and we need to see that okay, whether the next value E exists or not. So we need to check 3 places, not this one, because this already has the value hash, which means we won't check this one. But we in theory we might have to check at all 3 places, and imagine if all 3 of them had the value E, we might have to explore the paths on all 3 of them in order to find the next value R. So that is why at every single position N, we actually have 3 different options to see that whether this word exists or not, and this L is actually length of the given word. So that is why this is the time complexity. In terms of space complexity, we actually need to store the value inside our space until the time we reach to this entire word. So it would be big O of L, where L is the length of the word that is given. And this time and space complexity works perfectly fine, and I hope this solution makes sense to you. Let me quickly show you that what would be the coding for this one. So for this word search problem, we will actually have to create a backtrack public method that will call itself, and recursively we will try to achieve its answer. So there are some variables that we will need in both in this boolean exist method and also in the new backtrack method that we are trying to create. So let me define some variables that are global and that we can use in both the methods. And the variables we are going to create is to store the value of this board, and we will also need the row and column size of this given board character array. Now we have these, we will assign values to all these 3 variables from these given input endpoints. Once we have this, we will have to iterate over this board character array. So we are going to assign 2 for loops, and for both the for loops we are going to have the I and j value iterate up until the point of this rows and columns, and inside this for loop we will call our backtrack method. Now inside this for loop we are going to call our backtrack method, and we are going to have backtrack method return a boolean reply either true or false. And inside the backtrack method we are actually going to pass in the values of the current row position, current column position, word we are trying to find, and the index value we are currently at. So for the index value we would initially start with the position 0, and we would increment it every single time inside our backtrack method. And if at any case this returns true, we can simply return true in this case. And somehow if we are able to complete this loop and get out of it without returning true, which means word does not exist, so we can return false. Once this is done, now we will create our public boolean method called backtrack. Now first of all we will check that what is the condition where we will need to return true. So if at any point we identify that the index value is actually greater than or equal to word length, which means that we have already found that the current word already exists inside our given character array, so we can return true in this case. So now we will try to find the terminating conditions, and inside the terminating conditions, first of all we will check that whether the row and column position are they going out of bounds or not. If they are going out of bounds, we can return false immediately. If that is not the case, we will try to see that the current value we are looking at inside our board, if that value is not in sync with whatever the index value of the word we are looking for. If that is not the case, we can also return false immediately. So if any of these conditions are true, we can return false immediately. None of these conditions are true, which means that the current index value actually matches the value of that row and column position inside the board, and now we will have to iterate over the neighbors of this current row and column value inside the board. So in order to iterate over the values of the row and column, we are actually going to have two arrays called row direction and column direction, and that will help us navigate all the neighbors of any particular cell. Also, before moving to the next element, we are going to mark the current row and column position to have a value called hash, so we avoid checking the same element twice. Okay, once this is done, we will also have a boolean variable called return, and initially we are going to initialize its value to false, because basically we are going to call the backtrack function for all the four neighbors of the current cell. So for that we will keep track of this ret variable, and we are going to run a loop to iterate over all the directions, and we will add the values of these row direction and column direction to subsequent row and column positions inside this recursive call to our backtrack function. We will also update the value of the index, because we can determine that we have already find the word inside the previous index, and that's why we are calling the next index where value to be searched inside the neighbors of any given row and column position. And also at any point, if we identify that the answer of this return function is actually, or this return variable is actually true, we can break out of that particular element immediately, and we don't have to check all the other neighbors. So we will put that condition as well. Once that is done, basically we are done with the checking part. Now the only thing we need to do is we will have to update the value of the row and column position to whatever the value that was originally there, and in the end we can simply return whatever the answer we got for this ret function. This is pretty much it for both our backtrack method and also our main method, and this should be able to solve our problem. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code, and our solution works as expected. And I would be posting this in the comments, so you can check it out, the solution from there. Okay, so now we will attempt to do a very scary question that is called n queens. Now, in my opinion, this is one of the most toughest and most interesting problem I have seen. Basically, this one is a LeetCode hard problem, and very justifiably. It is also an extremely well-liked problem, and let's understand the statement. The n queen puzzle is a problem of placing n queens on an n cross n chessboard. So if we are given, let's say, 4 by 4 chessboard, we will have to place 4 different queens. Now we know that every single queen can iterate in 3 directions. Let's say that if I decide to place a queen over here, then this queen can control these squares, and these squares, because queens iterate in all 3 directions. So based on considering a formation such that I am able to place 4 different queens, and without these queens intersecting with each other on a given n cross n board, and I will have to make sure that I populate all the n queens. Now let's see that what else is being asked for this problem statement. That we are being told that we are given an integer n that defines that what is going to be the size of the board we are dealing with. Now we need to return all the distinct solutions to the n queens puzzles, and good thing for us that we can return the answer in any order. Now there is also one more just a quick note, that each solution contains a distinct board configuration on a place where the queens can be placed. Let's say that if I decide to place a queen over here, then next queen might be placed somewhere over here, because I need to avoid hits by this queen. So there can be one solution or 2 solutions or 3 solutions, no matter how many solutions are there, where I can place all 4 queens on this 4 cross 4 board. I will have to put all of those solutions inside the answer. Next thing is, we are being told that where we are placing the queen, we will mark it as cube, and where we are not placing a queen, we will just mark it with a dot. So let's first try to understand this problem with this given example of a 4x4 board. The idea is we are trying to place 4 different queens on this board, and we will have to explore all the possibilities we could in order to generate the answer. Now this is going to be a very long video, so I'm just warning you beforehand. I don't want to take any shortcuts, and I want to make sure that I understand this problem and you understand this problem. So now let's get started. Basically, let's start one by one. Let's say that I put the first queen naively on this very first location. If I do that, which means essentially I'm eliminating all of these squares for any other queen to pursue and use it as for their configuration. Let's say I put this queen. Now in order to put the second queen, I have two options. So let's say randomly I just pick this option. Okay, so once again, after picking this option, also these squares are now being controlled by this queen. Next thing is, if I want to put another queen, there is no place for me to put the third queen because this entire row has been covered because I put this queen over here. So let's try to revert that. Let me try to put this queen somewhere else. Okay, so let's say if I don't put this queen over here, then all of these squares would become empty. And once again, let me just try to put this queen on the second position and then try to see. So let's say if I put this queen over here, once again these squares gets controlled by this given queen, and now I only have one option in order to put the third queen, so I can put third queen over here, but that controls this option, which means once again I cannot put 4 queens over here. So once again I will have to go back, and I exhausted all the possibilities for the second row, which means I still have to exhaust more possibilities at the first row by changing the position of this queen. So let's try to do that operation. For that, I will have to clear the board and basically do a backtrack operation. Let's do that. And now I'm trying to place queen over here. Now, which are the squares being controlled? Let me just quickly mark each one of these to make sure that I don't create any confusions. Now for the second row, I only have one possibility where I can place my queen, so let me do that, and let me also mark all the items that are being impacted by this queen. Okay, now for the third row, I only have one option, so let me also place one queen over here, and once again exhaust all the possibilities. And now for the fourth row, I only have one choice where I can place the queen, and that is this empty square. So now we can see in this case that we are able to place all 4 queens on a 4x4 grid. So this is one of the potential solution. So we will actually have to mark this entire solution and place it inside our answer array. So the thing is, let's say that we create a list that is going to store all the answers. How we are going to take the snapshot of this is that we are actually going to create an array that is going to represent every single row for this given entire section, and for each of the row we are going to mark it as this, that we are going to store string values, where for the first 2 elements we don't have a queen, so we are going to mark them by dots, and then we do have a queen, so we are going to mark it by queen, and then we are once again going to mark it by dot. Once again we are going to do the same process, so queen and then dot dot dot. Once again for the next element, repeat the same process, so basically 3 dots and then a queen. And for the last one, we are going to dot queen and dot dot, so dot queen and dot dot. Okay, and so this becomes one of our answers. But the thing is, this is not the whole answer. We could still have more potential answers. So let's say we explored one possibility. Let's try to explore another possibility. And remember, once again, we are doing the backtrack operation. Going back to the very initial call, we already exhausted these 2 possibilities for the position of queen. So let's try to explore more paths. Let's say if queen is over here, then once again let's repeat the same operation. We are going to eliminate all the squares being controlled by this queen. The option is to place it over here. Once again eliminate all the options. Once again we can place a queen over here, and for the last one we can place a queen on this position. So once again this becomes another one of distinct answer, because notice the positioning of queens are different compared to our previous answer. So once again we are going to note this entire answer. Now don't worry, I will not put you through the painful process of going through the whole thing. Let's say that I just paste this answer over here as part of the next array list inside our answer, where we are going to return the list of array list. Okay, And now let's say we try to explore the very last option for the queens. Once again, for the very last option, we are going to be placing the queen over here. If we try to do this one, basically this solution would not work, because we would not be able to find appropriate queen positions in order to fill it out. So notice that in this case, once again, we filled out all these four possibilities because we placed a queen over here. If we don't do that, if we decide to place a queen over here, then once again we are eventually going to fill out all of these possibilities. So these are the only two distinct ways through which we can place all four queens on this 4x4 grid, and this is what we will have to return as part of the answer. So this is what is being asked us to solve. Now the thing is, let's see how we can actually solve this problem. So notice at the very beginning, when I selected a queen over here, immediately I did not started rejecting this option. Basically what we can do is that at every single position we have two options to make, that whether we can place a queen over there or we can not place a queen over there. Now we will have to explore both the possibilities, and in this case we will proceed in column by column area. So we will try to put the queen on the first column. Based on that, we will it will determine the position of the second column, and then third column, and then fourth column. So initially the idea is going to be that for the very first column on the leftmost portion, or the very first value, we will try to place queen. And let's say that after placing this queen, our logic would be that we will have to find an empty space in this particular section where the squares are not being hampered by this queen. We can completely ignore this entire column the moment we place queen at one of the position. So our jumping is going to be based on column by column level, and at every single column for all the n values, we will have to determine that whether it is a sufficient place to place a queen. And the moment we find the very first opportunistic moment where we can actually place the queen, once again we are going to repeat the same operation for the next subsequent column, and once again we will try to find an appropriate cell where we can actually place the queen. So there could be two options. One option is that, let's say that we are able to identify some place where if we just take a look at this example, basically in this example, if I place a queen over here, we exhaust all the possibilities. Now there are no place for us to place a queen, which means immediately it should come to our brain and also in our program that placing queen over here is not a good idea. That is option number one. Option number two is that placing queen over here is not a good idea. So we are going to do the backtrack operation, and after backtracking we will first try to remediate our this mistake, and we would, instead of placing queen, we would place at the second possible place, and once again try to repeat the same operation. But eventually this will also not yield us the correct result, and eventually we would keep on backtracking to our very first decision. And through the very first decision we would try to make sure that, okay, instead of placing the queen over here, let's try to explore other possibility, and then this would lead us to our correct result. So that is number one thing on we can understand that how we are actually able to find the answer. The logic is quite straightforward. We are simply going to do a recursive backtracking call in order to determine that whether the given path is a correct sensible path or not. But this is not as simple as it sounds, because there are a lot of computation and a lot of things we will have to understand and break down for our program to that how it is going to work. So let's quickly understand first that what is going to be the recursion we need to do in this case to complete the problem. Well, we know that for recursion we need two items. Number one item is that a base case, and second item is that we need a appropriate recursive function. Base case in this case is quite straightforward. The moment on the C4th column we find an appropriate location for the queen, we know that we already crossed all of these columns, and then we reach to the column 4 where we are able to find an empty slot for a queen to be put in. So which means this has to be the complete correct path that we are able to generate in order to fill the answer, and that is exactly what we are going to be storing as part of our base case. So what we will do is, number one, we will need some way to keep track of all the paths that we have taken so far. because by doing that we are doing two things. Number one thing is that when we do reach to that happy path scenario for our base case, we can actually add the path that we have stored for so long for the positions of queen as part of the one of the values for the answer. So that is number one thing. Number two thing is that using this path, let's say at some moment we decide that we cannot go further anyway, then once again we can just say that this path does not yield to the correct result. If it does not yield to the correct result, we can simply do a backtrack operation, and through the backtrack operation we will try to explore other paths. So just same way we saw over here that this q location was not working out, so we tried to see for this q location. Once again that didn't work out, so once again we updated from our q location this one to this one, and then we try to identify that whether this is the correct path or not. So we made some judgment calls through our recursive function on what are the things we are trying to achieve. Basically, don't get confused. We are just doing exactly the same thing that I showed you on the throughout the entire graph. The only difference is we are trying to do it recursively, and we are trying to follow both the things, that what is going to be the base case where we need to break out of the recursion and store the value to the answer. If we are not able to do that, then we will also have to do the recursion using the current path we are choosing in order to solve the problem. Now there are also few more things that we will have to understand. First thing is that at every given moment, whenever we are checking for potential candidates, we will have to understand that whether this path we are taking, if that is the correct path or not. Because let's say that in this case I place a queen over here, which means I am eliminating these elements that can ever be used for the potential queen. So now when I am at the column 2, I once again going to check all of these positions one by one, and in order to check that whether they are good candidates or bad candidates for my queen to be placed over here, I will need some method to basically do a validation that whether I can place my queen on this square or not. And the only way I can check is that is to check my current path that I have currently iterated over and see that this particular cell has it being impacted by any of the queens that I have previously placed. And by doing that, we can actually make sure and find the potentially good values for our queen. So let's say that we identified potentially good values for our queen. So we did this operation for this first column. Then once again we repeated the same operation for this next column. Once again we are going to repeat the same operation for this third column. So logically we are just redoing the same thing that we have done in the past, but for the different input. And that's where the second requirement for our recursion comes into the place, because remember recursion needs two items. First one is a base case and second one is a recursive function. So as part of the recursive function, whenever we are moving to the new column, we are simply updating the value of the column, plus we are also updating the value of where we have stored the queen in the previous value inside our current path. So this will allow us to do the backtrack and also allow us to move to the next value inside the logical iteration of our recursion. On top of it, that's why this is a hard problem, because there are a lot of on top of it that you will have to understand. At every given moment, once we reach to the very end, in the current path we are not keeping track of all the items of the board. We are just simply keeping track of the position of queen that we have placed so far in each of the columns. So once again we will have to have a method where we are actually generating the board based on the positioning of the queen. So remember that ugly board that we are seeing, like that contains dot q dot dot, then once again like dot 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 q, and this type of like Morse code type of structure. We will also need a method to generate this as well. And this is the solution. Basically this is the optimal solution in order to solve this problem. We are using backtracking, we are using recursion. For recursion we have a base case, we have a recursive function, we are keeping track of the current path we are at. We need to have a method to check that whether the given path is valid or not, to place the queen based on the previous queens we have placed. Plus we will need a method to generate the board that we need to generate in order to solve the problem. And in the end we need to store everything in an answer where in the answer we are actually storing the bunch of different arrays as part of the array. So it's going to be an array list that contains multiple array list. And if we try to calculate time and space complexity in this case, well, it's really difficult to calculate the time complexity, but let's try to understand the time complexity logic in this case. If you can understand this, then your logic to solve time complexity is going to be pretty beautiful. Logic is quite straightforward, that for every single column we are iterating over all of these values, and we are doing it for each of the columns, which means basically we are in the worst case scenario, we are iterating over each one of the elements. So basically and the number of elements we know are n to the power 2, and at every single element we have two choices to make, whether to include that element or not to include that element, which means we are actually doing 2 to the power of n multiplied by n, or 2 to the power of n square work uh, for this one. And we will have to repeat the same operation for each of the columns, because remember that in column 1 there are 4 possibilities that can lead us to different paths, which means we will have to calculate this for each one of them. So we will also have to do this operation n times. So time complexity is horrendously bad, and that's why if you read the problem statement on LeetCode, we are only being told that the value of n can only be between 1 and 9, nothing more than that. We are dealing with a very small number of finite solutions, because if you try to do this with million values, we need quantum computers in order to solve this problem. Okay, now let's quickly see the coding solution, and I hope my solution made sense to you. Okay, so the very first thing we are doing is that we only have value n that we need to return. So first of all, we are creating a blank board of n cross n size, and we are marking all the values as initially as dots, because we don't have any queens placed at the moment. We are also initializing a new array list of list called result, where we are going to be storing all the result, and then we are going to be calling our backtrack method. This backtrack method is going to do the backtracking and also recursive function for us. In the input, we are providing the new board that we just created, plus the starting index of the very first value that we need to iterate over, and the result array list that we have just created in order to store all the answers. Now let's understand our backtrack method. So very first thing we are doing is this is our base case, that if the current length of our column is equal to the length of the board, which means we have placed the queens correctly on all 4 columns or all n columns. So the correct current path or the current version of board is suitable enough for us to place it into the result. But the thing is, we are not directly placing it into the result. We are actually calling a construct method to construct the board we want in the subsequent manner. And first, let's just see the construct method. Okay, so in the construct method, we are just passing in the board. On top of it, we are checking that what are all the current positions of the queen that we currently have, and we are just adding those values as part of the queue. Apart from that, we are not doing anything else, and we are simply returning that to the result. Okay, next thing is so let's say we add the appropriate result over here. Then we have our for loop, which allows us to iterate over all the values inside our given input, where we are starting the value from 0. We are going until the length of the board, and we are just doing I plus plus. Very beginning, for every single board position, we are checking that is it a valid place where I can place my queen, and this is valid method is doing nothing but checking that based on the previous paths that we have calculated, whether we have any particular queue or any particular queen placed before, that is either in the row of that particular queue, in the column of that particular queue, or in the diagonal of that particular queue. If that is the case, we simply need to return false, that this is not a valid position where we can store our queen. If none of these cases are true, then only we will return true, saying that yes, this is a valid place where we can actually place our queen. So once we find a valid place, we update the position of our board to mark that value as q or queen. And then once again, so this is what this we are updating the current path, and then once again we are going to be calling our current recursive method with the new recursive call, where we already updated the current path of the board, and we also call in with the next index position or the next column we will have to iterate over, and we will keep on repeating the same process. Once we receive a call back from our board, we will also have to explore other paths that we haven't explored so far, and that's where this recursive call comes in, where remember, first we are marking this current position as cube, but next we are marking this current position as a dot, that this is no longer a cube, and we are exploring other paths. And this is the whole solution. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 87% faster than all the other solutions, which is pretty good comparing that how difficult question this one has been. Also in terms of memory usage, our code is pretty good, and in terms of like much better than a lot of the other solutions. Once again, the solution of this code is present on our GitHub repository. I highly urge you to go and check it out and try to solve this problem. If you can solve this problem, I don't think any backtracking problem would be a cause of concern for you. Okay, thank you. Hello friends, so now once again let's do an awesome LeetCode problem that is going to solve all of your problems. So without any delay, let's get started. So the LeetCode problem we are going to do today is called diameter of a binary tree. We can see that this one is an easy problem and also a very well-liked problem. The problem statement is quite straightforward. We are given the root of a binary tree and we need to return the diameter of the tree. Now the question is, diameter of a tree is the length of the longest path between any two nodes inside this tree, and we are told that this path may or may not pass through the root, but it's gonna pass through the root. Okay. Now the length of the path between any two nodes is represented by the number of edges between them. So let's try to understand that how does a diameter of a tree is being calculated. Let's say that we are given a tree like this. So in this case, what is the longest path we can make? Well, let's just give them the number. So 1, 2, 3, 4 and 5. These are the numbers of this given nodes. So we can see that the longest path over here is this one. So 3, 2, 1 and then 5. This is one path. Second longest path is once again 4, 2, 1 and 5. So in either case, the longest path we are able to make contains 3 edges. This is going to be the first edge, this or this, either one of them. Then this is the second edge and this is the third edge. So the answer is going to be 3, that this is what we need to return. Now the problem statement is quite easy to understand, but the thing is, how do we actually calculate the diagram? And if we start iterating over every single path and then try to find the answer, then this becomes a lot of complication. So we need to avoid that. And if you look at it from the other way, at any given moment or at any given node, the diameter of that node is nothing but the height on the left hand side. So left hand height and the height on the right hand side. That's it. This is all a diameter is. And we can see that in action over here, that the height on this left subtree is actually going to be 2, because this is the first level and this is the second level, and the height on the right subtree is going to be 1. So if we do 2 plus 1, the answer is going to be 3. So this is what we need to calculate. Now we need to understand that how we are actually going to be able to calculate that for any given binary tree. And for that we simply have to iterate over any given tree, nothing more than that. Now iterating over the tree is actually quite simple, and we can use the common logic of recursion in this problem. Now for recursion, we need 2 items. First item is a base case. So base case in this case is going to be that if the current node, if that is equal to 0, which means we have reached to the very end and now we cannot go anywhere further. So then we start to do the backtracking. This is the first base case. Now what is going to be the recursive equation or recursive scenario? Well, recursive scenario is quite simple, that at any given moment or at any given node, the height or the diameter of that node is actually going to be the sum of the left diameter and the sum of the right diameter. And same way, even at subsequent left node, the diameter at that node is going to be sum of the left diameter and right diameter, and that's how we should be able to calculate the answer we are looking for. So in this case, the height on the left hand side is going to be 2. The height on the right hand side is also going to be 2. So the longest path we are going to be able to make is going to be of size 4. And we can also see some examples of that. So one of the longest path starts from this node and then once again to this node, and once again to this node, and then once again to this node, and once again to this node. If we see the number of edges included, this is the first edge, this is the second edge, this is the third edge, and this is the fourth edge. So this is exactly what we are looking for in terms of finding the answer. So we also found out the recursive solution, that the diameter at any given node is going to be the sum of the left node and plus sum of the right node. Okay, and then we can have our recursive function to iteratively recursively call our entire tree and then return back the answer. So this is actually going to be the whole solution. We are simply iterating over the tree, calculating the height, and whatever the sum of the height is, we simply return that. If we see time complexity, in this case, the time complexity is going to be big O of n, where n is the total number of nodes that are currently present inside the tree, because we will have to iterate over every single node. And in terms of space complexity, well, this is also going to be big O of n, because we are using the recursion, and in order to store the recursive stack, we might use big O of n space. So if you want, you can also do this problem iteratively, and in the iterative solution, we actually don't have to do or use the stack. But the only reason I am using the recursive solution is because it's good to do it like recursively. It's small amount of coding and also looks cool. Okay, so now let's quickly go to the coding. So the coding solution is quite straightforward. We are going to initialize our variable maximum diameter, and we are going to have our method diameter of the tree, from which we are going to call our get height method for left and right subtree for the given root element. Okay, now this our get height method is our recursive method. So let's quickly see what is happening. As a part of the base case, we are having the scenario that if the given node is equal to null, we need to return 0. If that is not the case, then we are going to find the left height and the right height. For both, we are going to recursively call the get height method with the left child and with the right child. Now for every single position, we will have to check that have we reached a new maximum diameter. So for that, we are going to do a simple equation of the current maximum element or maximum diameter we have been able to find. If that is greater, or if we find that the current left and right side subtree's height is greater than the current maximum diameter we have been able to find, then we need to update the max diameter. If that is not the case, then we can simply leave the max diameter as it is. Next, we need to return the height that we have been able to find. So in the end, we are simply going to return 1 plus the maximum value of either left height or the right height. And why are we doing 1 plus? Because at any given root node, we also have to consider the node by itself before propagating the height to its previous level. So that's why this 1 plus is there. Okay, with every new level, basically we add one value to the height. And this is the solution. Let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. So our code runs 100% faster than all the other solutions, and that's because the code actually operates on a very simple principle, and it runs in 0 milliseconds. So that's why it's 100% faster. It's nothing magic. Now, once again, the coding solution is present inside our GitHub repository. Let me quickly show it to you that this is the GitHub URL where we have actually stored hundreds of LeetCode questions and their answers. These are some of the most popular questions in the entire world. These questions has been asked at tons of different companies multiple times. So for each of the problem, you can go ahead and see we have the Java file for that. You can go and find the LeetCode link. If you don't find, you can also find the subsequent video solution, and also a list of most asked problems at the FAANG companies, which is this list, which contains a lot of important LeetCode LeetCode problems, they have been differentiated based on the topics. And for each of the topics, I have provided that how many times they have been asked at different top tier IT companies. So there are 130 of most fabulous questions that I have been able to find. Then also I have solved most of the LeetCode 150's problems, and they are also provided over here. So this, both of these resources are amazing. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do binary tree maximum path sum lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, DoorDash, Facebook, Microsoft, Google, ByteDance, TikTok, Snapchat, Twitter, Apple, Uber and LinkedIn. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So despite being a hard problem, this is a very well liked problem on LeetCode. Basically, we are given the root of a binary tree and we need to return the maximum path sum for that particular non-empty path. So we will have to understand a couple of terminologies over here. We will have to understand that what a path sum is, and before we understand that, we will have to understand that what a path is. Lucky for us, we are given definition of both of them. So a path is a binary tree sequence of nodes where each pair of adjacent nodes in that particular sequence has an edge connecting them, and we are also told one very important thing, that any single node in that sequence can at most appear once. We are also given the note that it is not necessary that path has to go through the root of the node. Okay, so over here I have drawn a couple of different trees and I'm going to show you some examples of what a valid path is and what an invalid path is. So first of all, this is a valid path. And for that we'll have to understand that why this path is a valid path, because all the three nodes that are connected in this particular path, they are adjacent to each other. They all have an edge connecting to them and they all appear at most once and nothing more than that. Now this is also a valid path and this is also a valid path. This is also a valid path and this is also a valid path. Both paths are valid as well. And the path that looks like this is also a valid path, and the path that looks like this is also a valid path. Now let's see some examples of an invalid path. Suppose I start up my journey over here. I go up, I go down, I go to the left child, and then again I try to go to the right child. Again, this is an example of an invalid path because this node appears twice as well. Now we know many examples that what a valid path is. Now let's see that what the problem is actually asking us to solve. After understanding the definition of a path, we are going to understand the definition of a path sum. Basically, it is the sum of all the nodes that are present inside this given path. So that is actually quite simple to understand, and the problem is actually asking us to find the maximum path sum that we can make out of given binary tree. So now I have drawn three different trees to understand the maximum path sum for each one of them. So first of all, for this particular tree, the maximum path sum is going to be this path. And why? Because all the nodes are positive, and if we take the sum of these three nodes, it's actually going to be 5 plus 4 plus 9, which becomes 18. And this is what we need to return in the answer. If we take the second example, things are not as easy as the first one. Why? Because we are dealing with a negative value over here. So in this case, even if we try to do the same path that we had drawn over here, this won't work because the sum of this is actually going to be, which is not the most optimal path we can achieve. The most optimal path in this case is going to be this one and the sum is actually going to be 5 plus 4 equals to 9, and in this case we will have to return 9. So in this case, the maximum path actually is going to be this one between these three nodes. Why? Though there is a positive value over here, if we were to include this positive value, the path we would make would looks like this. And that would actually go through this root value, which has the value of negative 11, which actually brings the total path down or total sum down. So that is why it is not in our best interest to include this node, and that is why the maximum path in this case we can achieve is amongst these three nodes, where the sum is actually going to be 10 plus 8 plus 2 equals to 20, and that is what we need to return. Now before we come up with the optimal solution, I'm going to show you a few different concepts with various examples. So first of all, we have an example of tree that looks like this, where in this case all the nodes are positive, which means things are a little bit easy for us, and our aim is to find the maximum product sum we can achieve, right? So the idea is at any given portion we have the root information. Now from this root information, what we are going to do is we are going to see that what this left subtree has to offer and what this right subtree has to offer, and then addition of all of them should give us our maximum product sum. So in this case, this left subtree does not have any more children. It only has one node, which means it can, the maximum value it can contribute towards the maximum path sum is going to be 5. So we have the value 3 already from this root. Then we gain this 5 from the maximum path sum, and then again we gain this 2 from this right subtree. So the total maximum path sum we can achieve is going to be 10, which is the answer in this case. And since all nodes were positive, it is in our favor to include all the nodes. So that is one way to do it, right? And this is a very simple example, so we are able to understand it quickly. Now let's try to see that what would be the approach in a little bit more difficult scenario. So suppose we are given a tree like this. In this case, we actually have a negative value. So if we apply the same logic over here, this left subchild has -5 to offer, this right subchild has +2 to offer, and this root value is actually 3. So maximum path sum based on the previous logic would actually become 0 if we just do sum of all the values. But that is not what we are going to do. We are also going to check at any given moment that whether the value that is being contributed, if that is less than 0 or not. If that is less than 0, immediately we are going to discard this value, which means that we are not going to consider this -5 to be part of this maximum product sum. And in this case, what we are going to do is we are going to do this 3 plus 2 because both values are positive. So in this case, the answer we are going to get is 5. So we gain one more important thing, that whenever we see minus values, we are going to ignore that from our maximum production because they don't add any more value over here. Now one more thing we need to consider. What if we have multiple nodes, and then what should be our approach in that case? Okay, suppose we are given an example like this. In this case, what should be our approach? Well, we want to find the maximum path sum. So again, we are going to repeat the same process. We are going to see that for this root node, what is this left subtree has to offer? It has to offer maximum 5 value. So we are good up until this point. For this right subtree, actually we will have to calculate that what is the maximum value it can offer. And how we can do it? We are actually going to take this root value because that is going to be the part of this right subtree for sure. So we already have value as 8 over here. Now from this 8, we actually have two options to be included for our maximum path sum. We can either do 8-2 or we can do 8-1. So in this case, obvious choice is going to be 2 because this value 2 is actually greater than with this value 1. So in this case, we are going to ignore this 1 and we are going to keep this 2, which means that we can do 8 plus 2 to be 10. So in this case, we can determine that this actually has the value 10 to give towards maximum path sum. Now the question will come to your mind is that why in this case we only choose value 10 and why not we chose value 11? Well, what if under what circumstances can this value become 11? It can become 11 if we include all these three values to be part of this maximum path sum. But we already know that this goes through the root value, which means that if we were to include all these three values to make the value 11, it won't work, because then the path would look like this. It would go from 5 to 3. Okay, so far we are good. Then again through 8. Now from this 8, we cannot include both 1 and 2, because suppose we try to do it, we include this 1 and then we try to go back to 2, we come up at this 8 again, and we know that that cannot be part of a path sum. So that is why we only have the option to choose either 1 or 2. So that is the important detail over here. That is why for when we were calculating the maximum contribution this right subtree can make, we only had two options. Either we could do 8 plus 2 or we could do 8 plus 1, but not both of them. So just remember that. That is why I showed you this example. So in this case, the maximum contribution we can get from this right subtree is going to be 10. So now let's calculate the maximum path sum in this case. So the maximum path sum is going to be the root node is 3 plus this left subtree can contribute value 5 and plus this right subtree can contribute value 10. So the answer is going to be 18, and this is what we need to return in this case. So far we have understood, we had gained very good understanding of many different cases. Now let's consider one more case where the things become a little bit more interesting. And why it becomes interesting? Because so far we are under the impression that we have to take this root value as part of the answer. But what if that is not the case? What if we encounter some possibility where this root value does not need to be part of the main maximum path sum that we take? Then how do we approach that? So let me quickly show you an example for that as well. Okay, this is the last complicated example. Now in this case, we are again going to apply the same logic to find the maximum path sum, but we are going to do some interesting things. So first of all, we have this root value to be minus 3, right? Now we are going to see that what is the leftmost contribution it can get. It can get 3 as the contribution in this case. Now again, for this portion, we are going to see that what is the rightmost contribution it can get. The rightmost contribution it can get in this case is going to be this 8 plus 2. So 8 plus 2 is going to be 10 so far, right? Now if we see over here, actually this is not the most optimal way to approach this. Why? Because this path actually gives us the maximum path sum. So let's see that how can we actually determine that. Well, when we are traversing, we are actually going to have a variable called path to keep track of what is the current maximum value we have found so far, and whether do we need to include a new route. And new route in this case is going to be the condition where we actually refrain away or move away from the original route we were using, because if we were to use this root node, there is no way for us to use all of these three nodes. So that's why what we are going to do is, we are first of all going to see that if we use this current root, what is the maximum value we are gaining. So the maximum value we are gaining in this case is going to be 3, which is this one, plus 10, which is the contribution we can get from this right subtree. So 3 plus 10, and let me get rid of this maximum path sum for now. So 3 plus 10 plus whatever the root value. So root value in this case is minus 3, which is in this case the total value is going to be 10. But now when we are traversing, or when we were calculating the maximum contribution we can gain from this right subtree where the root node is actually 8, the value maximum we can gain from over here is actually going to be this value 8 plus it has the its left subtree is contributing value 1 and its right subtree is contributing value 2, so which both are positive values, and their total is actually 11. So this is 11 and this is 10. Then why are we so keen to keeping this root to be part of the optimal solution? We should not put it in the maximum path sum, and this is exactly what we are going to do. Then we are going to choose a new path, and this new path, the value is 11. So then we are going to have a maximum path sum variable where we are going to keep on updating the value, and we are going to update the value to be 11, and now it does not have any further no more nodes to check for, and then we are going to return this 11 to be the answer. And at any given moment, whenever we find that the new path we are getting that gives us better answer than whatever the previous answer we were getting, then we would update the new path and we will update the value of the path variable. So that is one tricky part that we have to understand in this question. And now let's see that after understanding all the concepts, now let's see that what would be the way to solve this problem. The idea is, let me clean this up a bit. Now I'm going to use the same example to quickly walk through this problem. So first of all, we are at this root position. What is the left contribution we can get, which is 2. The right contribution we can get, in this case it's going to be 10. We actually calculated all of them. Now the sum of these these three is actually going to be 10 only, but when we were calculating that, we had this path variable where we actually calculated the value of this to be 11, and we updated this path variable. And then we are going to have this maximum path value where we are going to keep track of the maximum path we have found so far, and in the end, because it does not have any more children, we are going to return the maximum path to be 11, and this is what the answer we need to return. So basically we are taking a bigger problem, and then we are dividing it into bunch of different parts. That for this root we are actually trying to calculate this left subtree and right subtree. Then again for this root value, we are again calculating this left subtree and right subtree, which means we are solving this problem recursively, and that is how we are going to approach it. And also let me show you the time and space complexity. So time complexity in this case is actually going to be big O of n. Why big O of n? Because at any given moment we will have to iterate over all the nodes that are present inside this given tree, and the space complexity is going to be big O of h, where h is the height of the tree. So first of all, we will need a separate method called max gain to calculate that what is the maximum value we are gaining. So for that we are going to create a new method that takes in a node as an argument. We will also need a maximum sum value. So we are going to initialize it as global variable. We are going to assign it to the most negative value possible. So okay, now let's start implementing our max gain function. So first of all, we are going to have the terminating case that if the given node is equal to null, we will return 0. If that is not the case, we will need the values of left gain and right gain for any given tree node. So we are again going to call the recursive function for that. We are going to create a variable called price new path that we are actually going to calculate by using the node value plus whatever the sum of left gain and right gain is. Now that is done, we are actually going to calculate the max sum. We are going to compare it with whatever this new path we are calculating. And once that is done, basically all we will have to do is simply return the node value with whatever the maximum value is amongst this left gain or right gain. From this max path sum method, we will have to call this max gain function. So let's do that. After all the calculation, we are simply going to return whatever the max sum we are able to achieve. Okay, and now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our solution is actually pretty efficient and faster than a lot of other solutions. And I would be posting this in the comments so you can check it out from there. Hello friends, hope you are having a fantastic day today. So now we are going to do a very popular LeetCode problem. So without any delays, let's get started. So the LeetCode problem we are going to solve is called symmetric tree, and we can see that this is a LeetCode easy problem and also a very well-liked problem on LeetCode. The problem statement is very straightforward. We are given the root of a binary tree and we need to check that whether this binary tree is a mirror of itself or not, which we can see it from the example. Where notice that ignoring this root node, if we compare the subtrees of this root node, we can see that they are exact mirror copies of each other, which means this left node is same as this right node. Once again, this left node is same as this right node, and once again, this right node is same as this left node, which means we need to check that for any single given tree, whether this symmetric property is true or not. And this is actually very simple to do. So we are just going to do what we just used to explain this problem. If we understand we are given the root, then since this is a binary tree, it can either have a left node and right node, and once again this left node can also have a left node and right node, and same goes with the subsequent trees, and there can be many layers as we want. The only condition we are checking is that for any single root value, we can only say that the tree is symmetrical if its entire left subtree is also symmetrical with entire its right subtree. And in that case, we need to check that whether the left child is the same as right child. And once again, even at this subchild level, we need to check for the grandchildren. So once again, even at this level, we need to check that whether this left tree is same as this right child, and also this right child is same as this left child. If that is the case, then we can determine that this is a symmetric tree, and we can keep on repeating or going down as many levels as we want, but the core logic remains the same, which means number one, we are doing two things. Number one, we are taking a bigger problem and we are actually breaking down into sub problems, and we are keep on repeating the same process for all of its children. So we are going to be using recursion to solve this problem. That is number one thing. Now number two thing is that we know in the recursion we need two items. Number one thing is that what is going to be the base case. So base case is quite simple. If any particular child does not have any more children, or if there does not exist any left or right node to check, then we can get out of the loop. And if we do get out of the loop and everything remains the same, which means we can return that this is a symmetric tree. That is option number one. Option number two is that at every given moment, we need to have a recursive function based on which we are going to be making our recursive call. And what is going to be the recursive function in this case? That at every single root node, we need to check that whether the left child of root is same as the right child of root or not. and we are going to be keep on repeating the same process. Once again, at the root node, we are going to check that whether the left grandchild of the root is going to be the same as the right grandchild of the root or not. So this is going to be our base case, that the left child is equal to right child and right child is equal to left child. This condition has to be satisfied, and then only we can keep on repeating the same process in the recursive manner. And basically that's it. So just the way I explained that, let's understand this with some example. So suppose we are given a value like 5, and then we are given subsequent values 3 and 3, and once again we are given further subsequent values. Let's assume like 4 5, and then this is also 4 5. So is this a symmetric tree? Yes, this is a symmetric tree, because both of these values are same. This is also equal to this one, and this is also equal to this one, which means in this case we can return true. If we are given some other value, let's assume that over here we are given one extra child like 6, then we cannot complete the recursive call, because this right subchild still also has a left subchild, but that is not present over here. So we can say that this is not symmetric. But in this case, if we did had another child like this, then we could have said that this is also symmetric. So this is the logic that we are going to apply. Now let's see the coded solution for this one. So first, this is the definition of our tree node, where every single node has a value. It has a left child and it has a right child. Now let's see our solution. So for our is symmetric method, we need to return true or false or boolean value, and in the input we are given the root of the given existing tree node. Now first we are going to check for the edge case, that if the given root is equal to null, we can simply return true. If that is not the case, we are actually going to call our recursive method, that is called isMirror, where we are going to pass in the left child and right child of our root node. Now let's see the recursive method isMirror. So as an input, we are having two tree nodes. So first condition we are checking is that if the given left is equal to null and right is equal to null, so both of these entries are null. If that is the case, we can simply return true, that saying that the tree is symmetric. If that is not the case, we are also going to check that if only one of them is null and the other one is not. If that is the case, then the symmetry has been broken down, so we can directly return false. If none of these cases are true, which means we still have to perform our iteration. So first we are going to check that if the given left dot value and the right dot value, so value of this left node and the right tree node, if both are same, then we are going to recursively call this isMirror method. For this isMirror method, we are going to take the left child of this left tree and we are going to compare it with the right child of this right tree. And same way, in the next iteration, we are going to compare the right child of this left tree with the left child of this right tree. So I know that this portion might look confusing, but if you just try to understand this using the image, things will become much more simpler. And I forgot to mention one thing during the code, that this code actually runs in big O of n time, because we are simply iterating over every single node just one time, nothing more than that. And in terms of space complexity, this is also going to be big O of n, because in order to fulfill this recursive stack, we might have to use big O of n space. Okay, so let's try to run this code. Okay, our solution seems to be working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions, which is awesome and pretty good. So once again, I would be posting this solution in the GitHub repository where we have, which contains all of the LeetCode problems that we have solved so far. Also, I wanted to show you one more thing that might be helpful for your preparation. That is this Google document that I have created, which contains information about some of the popular courses that I have created. But this is the most important part. This is the collection of 130 most popular, most asked and most promising questions that has been asked at interviews. I have broken down these questions based on different topics. And also I have provided the information that how many times these questions were asked at specific companies. So this is going to be really helpful if you are targeting any specific companies, or if you are just targeting different topics, or depending on the different difficulty level. So if you want, you can start leveraging this, and I would be posting the link of this document inside the description of this video, so you can easily check it out from there. Thank you.
Hello friends, the problem we are going to do today is one of the most versatile, most asked question in the history of LeetCode questions. Like if you just look at the sheer numbers of the amount this question has been asked and the range of companies this question has been asked, it's just mind-boggling. Whatever your dream company might be in the entire world, and if they do good technical interviews, they must have asked this question probably at least 2 3 5 10 times to their candidates. If I only had 10 minutes to prepare for a technical interview, I'm going to choose this question at the top of my choice. Like just look at the companies over here, like Amazon, Microsoft, Bloomberg, Facebook, Google, LinkedIn, Oracle, Apple, ByteDance, which is basically TikTok, DoorDash, Yahoo, Paytm, Walmart, Tesla, Samsung. So I doubt that there are any companies left that didn't ask this question. And the question we are going to do today is number of islands, and I'm going to pay my utmost attention to this problem. Now in the input problem, we are given a grid of m cross n as a 2D binary matrix, and in this particular grid, we are all the cells are filled with either values of 1 or value of 0, and whatever the value that represents as value of 1 actually represents land in the real life, and all the values that are marked as 0 is actually water. And we need to find that what are the total number of islands inside this particular grid. Now based on the definition, we know that suppose if we have some sort of body of land, something like this, and if it is entirely covered by body of water, we can say that this particular body of land is actually an island, and we that is what we are trying to find in this given problem. Now we are also told one more thing, that at the edges of this particular grid, like all of these values, this is also water, which means that suppose we are given an input like this, where all of these values are zeros, and we only have just one single one over here, this we can also conclude as an island, because on these three sides of the island is already water, and on the outside is also water, because we are told that everything on the outside is also water. So just keep this in mind, that if we find some place at the edge of the grid, we still consider it to be surrounded by water if all the other side inside the grid is also water. And our aim is to find that how what is the maximum number of islands that are present inside the given grid. Now this problem is actually pretty simple. Like if we just see over here, like in this particular input, if we try to find for this example one, that how many number of islands there exist, actually there only exists just one island, and that is this one. Because notice this, that these all ones are actually able to be connect with each other because they're adjacent to each other. If for any particular cell, suppose this is marked as 1 and this is a part of land, and any cell adjacent to this cell is also marked as 1, we can say that both of these are a common part of land, because there does not exist anything in between. They are right adjacent to each other, and this is what we are given over here. So in this example, we can only find one island. Now if we take the second example, we can see that there are actually more than one islands. So this is the first island that we can find. This one is by itself, and if we see all four sides of it, this is 0, this is 0, this is 0, and this is 0. So this is also an island, and these two ones, they are also an island. So in this example, we actually have three distinct islands. Okay, suppose we are given a custom example like this, and I have mentioned in my previous videos that it is really important to come up with your own custom examples, because it shows that you can think on your own and you can create test cases on your own. It's a really important skill for any computer engineer to have. Now suppose this is the grid that we are given,
and this blue line indicates the body of water we have outside of our original grid. So this is just for understanding purposes. I'm just going to get rid of it now so it does not become an issue and I can explain the problem better. So we know that there is water outside. Now the most basic approach is that we start traversing through the entire grid in some manner. Like there are bunch of different ways to traverse through the given grid, and we try to see that at any moment if we find one, which means that so far we have find a body of land. Now since we have found this one, we need to see that what are the different islands we can create, and we can create bunch of different islands if all the values are relate are connected with one. Like no matter how many number of values are connected with any single one, we would mark all of them as just one island as long as they are connected with each other. And basically what we are doing is we are trying to find separate set of ones. Understand what I'm saying? We are I will repeat, we are trying to find separate set of ones. So in this example, if we just see that how many different sets we can find, like we can find this one set of one, we can find this another set of ones, and we can find this third set of ones, and over here we only have one individual element, but still that is a set on its own. Like even if we only have just 1 acre of land, it's still a piece of land which we can consider as island. So that is what we are trying to find. And let me just revert back. Okay, so now we know that what we are trying to find. The most basic approach is we start traversing through the given input array, and we start traversing. Okay, suppose we traverse the first row, we don't find anything. Okay, now again we start traversing over here, we don't find anything. Now at this point we find that okay, there exists an element 1 over here. The moment we find that there exists an element 1 over here, we are going to call our function, and basically what that function is going to do is it is going to iterate over all the adjacent cells, and it is going to keep on iterating till we exhaust all the ones that are connected with this one. So till we exhaust all the sets that are associated with this particular one. So let me just go back a bit, and this is the approach we are going to take. That initially, currently we came to this particular item, we find that okay, there exists a 1 over here. Now because there exists a 1, we need to find all the ones that are connected with this one. So what we are going to do is we are going to mark this coordinate, and once we have this coordinate location, first of all we are going to increase the number of islands we have. Like initially the number of islands we have is 0. Now because we find at least a single one, which means that we have found at least one island, so we will update the number of islands we have. Now since we have already updated the number of islands, and we already have coordinates for this one, first of all we will mark this one as 0. So let's mark this one as 0. Okay, and now from this coordinate we will try to find all of its neighbors to see that there exist any adjacent ones. So over here we find that okay, this one is also 1 and this one is also 1. So we are going to repeat the same process, and remember, we are not going to update our islands in this case because we are still connected with whatever the previous value we had found before. So we are still in the same set of 1 that we were dealing with, so there is no point in updating that, but we have to exhaust all the ones that are connected with this original one we had found before. So we will check over here. Okay, this is 1. So because this is 1, we will will change its value to 0, because it now it becomes part of this original set we had. Now again we are from here we are going to repeat the same process. Okay, we don't find any ones from this point, so we are good. But remember, over here we didn't exhaust all the possibilities from our original coordinate, so we still have to do some work. So again we will come back, we will find 1 over here, which means we will have to turn it to 0. So we will convert this 1 to 0 as well, And now from this particular position we will try to repeat the same process. So we will check all of its neighbors, and all of its neighbors in this scenario are now 0, which means we are good. Like we have at least exhausted some possibility, and we have at least found one set of island. Okay, now we will again repeat with our process. And notice that I convert all these three values to zeros because we already found an island over here. And now we will repeat the same process. So again we will start traversing our matrix, and over here we encounter the 1 again, which means now we have encountered a new set of island. So we will update the value in our islands. We will update this to 2. Again we are going to repeat the same process. So first of all we will update this one to 0, and now this is 0. We still have to check its neighbors. We find an adjacent neighbor. Again we flip it to 0 first, and again we go to the next element. Again we flip it to 0, and now we won't find any more neighbors that are basically 1, which means that again we will start traversing. So we keep on traversing over and over and over, and we don't find any ones. But now we are at this point. Again we find a 1. We update our island, so our number of island becomes 3. And now we need to find all the neighbors that are present in this particular island, and we set up all of those values to 0. So these values are set up to 0, and now we check that okay, no neighbor actually has a value of 1, which means we have exhausted all the possibilities of number of neighbors that could be a part of the island. And now again we repeat the same process, and now we find this one, and this is the last element. So again we increase the number of islands that we have found to 4, and we set this up to 0. And now because we have exhausted all the possibility and we reach to the end of the grid, we can simply return whatever the value we find in the number of islands, and that would be our solution. Suppose we were given an input with all the zeros, like over here we wouldn't have found any island, and we can simply return 0 in that case as well. But this is like a very basic approach, and the approach we took in this scenario is actually depth first search to find the set of ones that are adjacent to each other. Like we could have used BFS as well, but I mentioned earlier, like I'm trying to learn graph theory, and first I'm going to master DFS, then I will start working on the BFS. So that's why I decided to choose the approach of depth first search in this scenario. Okay, and the time complexity in this case would be actually big O of m cross n time complexity, because that is in we have to iterate over entire grid that is given. And the space complexity would also be big O of m cross n in the worst case scenario. Suppose that we are given a grid where all the values are just ones, which means that for any single element we will have to iterate over all the entire grid, and that could be the worst time and space complexity. First, we'll create two parameters, row and column, to calculate the current row and column values for the given grid. Okay, and we'll also create a variable called island, and initially we will set it up to value 0, and we would update this every time we encounter 1 inside the given matrix. And inside the loop we will have a condition that if the current I and jth position inside the grid is actually equal to 1, then only we are going to call our DFS function. So first we'll do island, we'll increase the value of islands, and now we'll call our DFS function. In the DFS we are going to provide the ith position, the jth position, and we'll also provide the grid that we are working on. And once this loop ends, like we should have all the set of separate ones, and we should have all the values of the total number of islands. So we can simply return the number of islands we have found. Okay, now we need to create the logic to implement this DFS function. So first we'll create a function. So inside the function we will need the values for the row and column again for the entire grid. So we'll just name them new row, and this would be grid's length, and we will also create a parameter called new column. This would be the first position's length. And this is basically the same as finding the row and column we found over here, but we need to use it, so I'm just giving different names. We'll also create a 2D array of called directions. This would make our lives easier and allow us to iterate over all the adjacent values of any current position, and we are going to initialize it with default values. We have this established. First we will put a condition that if the current row and column are they out of bounds or not. We will also put an additional condition that if the current value we are at inside the grid, if that is already 0 or not, because if that is already 0 we won't have to do anything. So if any of these conditions satisfy, we can simply break out of the DFS function, and this would be our terminating case. If this is not true, first of all we will update the current position we are at inside the grid, and will enter the value as 0, because remember we have already updated the islands. And now we will just run a for loop and iterate over all the 4 directions. So that will allow us to go over all the neighboring candidates of this row and column that we have. And now we are simply going to call DFS on row plus direction of 0 and column plus direction of 1, and we'll also provide the value of grid as well. And yeah, I guess this should be our logic, and we can try to run this code. Okay, looks like we messed something up. Oh, okay, seems like our solution is working. Let's try to submit the code. Seems like our solution is also working, but it's not the most efficient solution, and I'll try to make my solution better, because maybe there is some other way we can solve this problem, and if I find out, I'll probably make a video on that sometime in the future. Meanwhile, let me know in the comments if you have any thoughts regarding this problem. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, Pacific Atlantic water flow. And as you can see that this problem hasn't been asked in too many companies. The thing is, the companies where this problem has been asked are really one of the most important companies in the world. Google, Amazon, Uber, Microsoft, Facebook, Apple, ByteDance, which is a parent company of TikTok, Bloomberg. So you can understand the scale that why this problem is important and what kind of companies ask this problem. And the thing is, main intention for understanding this problem is to not to understand the actual problem, but rather the approach behind the solution, because that can become a base foundation for too many other problems. There is a lot of information in this problem statement, but if we try to comprehend this using the picture, it's really simple to understand. So I'm just going to go over that. Essentially, we are given a grid like this, and we are told that this is actually an island on somewhere in the ocean. But the thing is, it is at the cross junction between Pacific Ocean and Atlantic Ocean, and the way it represents is that this top and this left edges, they are actually Pacific Oceans, and this bottom and this right edges, they are Atlantic Ocean. So this, and the second information we are given is that all of these coordinates inside the given island represents the height of that particular area.
And why the height is important? Because we are told that on this particular island, on this particular grid, there happens to be a lot of rain, which means that rain falls, and we know the property of water that it gets transferred from higher height to lower height. We are also told that that rain at any particular cell can can go to four directions. It can go to top, right, bottom, or left, which means it cannot go diagonal in any scenario. And the condition that if it can traverse from one cell to another cell is that if the height at any particular given cell, if it's greater than or equal to the cell we are trying to reach, then the water can travel to that cell. Which means, suppose we take this cell for an example, the height for this cell is 4, which means if the rain falls on this cell, we can conclude that the rainwater will go to cell 3. It will also go to cell 1 and cell 2, but it would not go to this cell 5 because the height at cell 5 is greater than cell 4, which means that this is cell 4 and this is cell 5, so water can't travel like this. Now, the interesting part for this question is that we need to understand that what are the cells in the given grid that can travel, where if the rainwater falls, it can travel to both Atlantic Ocean and also Pacific Ocean. So let me clean this up a bit. Suppose we consider this cell number 5, and if rainwater falls in the cell number 5, let's see that can it reach Atlantic and Pacific. Like, we know it can reach, but in this cell adjacent to the cell number 5, the height is 3, which means water can go over here. From this 3, the water can go to this 1, and because this is at the edge of Atlantic, of course water can go to Atlantic Ocean from here. Now from this cell number 5, we know that water can also go on this side because the height is 4, and from this 4 the water can go because the height is 2, which is less than 4, and from this is at the edge, which means that at any point whatever the height over here is, like 1, 2, whatever value, all of that can go to Pacific Ocean. So we can conclude that water from this cell number 5 can reach to both Atlantic and Pacific Ocean. Let's take another example. Suppose we take an example of this value number 4. So we know that from this cell we cannot go over here, we cannot go to 5, but we can go to 2, and from 2 we can go to Atlantic. So that concludes one option. Now let's try to see that can we go to Pacific Ocean. So first, if we try to go on top, okay, we can go over here because this is 3, but from 3 we cannot go to the top because this is 4, so we can't go Pacific in this direction. If we try to go over here, we can reach to this 1, we cannot go to this 7, which means that from this 4 we can go to Atlantic Ocean, but we cannot go to Pacific Ocean, so we wouldn't include this in our intersections. For every single cell, we are going to check that whether it can reach to both Pacific and Atlantic Ocean. If it can reach, we will just maintain a list or some sort that will take care of all the cells that we are able to reach to both the oceans, and we would keep on adding them in this list. So first we'll start with this first element. We know that it can reach to Pacific Ocean, but it won't be able to reach Atlantic Ocean because height over on both these cases are greater, so we wouldn't include this. We would go to next one. So over this again can reach to Pacific, but it cannot reach to Atlantic because it will traverse in these two directions, but it won't be able to go any further over here and over here. Same happens for this one, and basically this solution would work. We would find our answer. Eventually our list would be filled out. Suppose we are at this location 5, so we know that this is at the exact intersection of both the oceans, and it can clearly go to the rainwater can clearly go to Pacific and both Atlantic, so we would add this particular location in our list, and eventually the list will be filled out. But the thing is, the issue with this approach is that in terms of time complexity, we are actually doing a lot of repetitive work, because for every single cell we are checking all the possibilities, and we might end up doing, in the worst case scenario, big O of. So suppose this is M and these are N cells, so we can say that the time complexity would be big O of M multiplied by N
squared, because for every single cell we will have to iterate over all the other cells, and this is not a very good time complexity. There exists a better approach. So in order to solve this problem, we are actually going to use a different approach, and the approach we are using is actually, if mountain cannot come to Muhammad, Muhammad will have to come to mountain. And what I'm trying to say is, suppose that rather than checking at any particular cell that whether it can reach both Atlantic and Pacific Ocean, we create two separate grids. So suppose we create a grid and another grid, so two separate matrix of Boolean values that has the same size of whatever the input size we are given. And at any particular location, we just name that okay, this matrix consists the data of all the cells that can actually reach the Pacific Ocean, and this cells contains this matrix contains all the data of all the cells that can actually reach to the Atlantic Ocean. And once we have these two matrices defined, the moment we find that okay, so over here we know that this particular element 3, this can reach to Pacific Ocean. So over here, suppose this value corresponds to this 3, so we will set the value as true over here. And same goes on this side, that suppose we find out that this particular element at position 4 can reach to Atlantic Ocean via this way. So whatever the corresponding value we have over here, we will set that value as true, and eventually we will have the entire matrices filled out. And once we have those, all we need to do is just intersect both of them and find the common elements between both of these matrix, and that would be our final list of matrix that contains all the cells that can reach to both Pacific and Atlantic Ocean, and this would be our solution. Well, this solution actually works pretty fine, it's pretty efficient, and all we need to do is we need to figure out that how we are going to generate these two matrix and what are all the different logic we are going to take. Let's take the most basic approach. I'll be showing you an example that suppose we want to reach to Pacific Ocean, how can we fill out that matrix. Now, what is the most basic thing we know about Pacific Ocean? Well, we know that for this particular island, all the cells that are present in this row and all the cells that are present in this column, they are actually at the edge of the island. Also, they are at the very adjacent to Pacific Ocean, which means all the water in these positions can actually reach to Pacific Ocean in all the cases. So in our matrix, whatever matrix we have, we can basically define all the elements these positions as true, because we know that they can reach to Pacific Ocean. Now, previously at any particular location, we were actually trying to go outwards to see if water can reach to adjacent cell or not. But rather than going outwards, why don't we come inwards from the cells we already know that can reach to Pacific Ocean? So over here, these cells we already know that they can reach to Pacific Ocean. So if we check that whatever the cells that are adjacent to these cells from this particular cell that can reach to Pacific Ocean, can we reach to these adjacent cells or not? And the moment we find that okay, we can reach to some adjacent cells that we haven't already visited, so we can set that as true. Suppose the value over here is 3 and we know that this is able to reach to Pacific Ocean, and suppose the value adjacent to this one is actually 6, so we know that since the height difference, there is a height difference, and over here we need to check the reverse height difference. Previously in this approach, we were actually checking that whether the height we are currently at and the adjacent cell is actually the height is lesser than whatever the current height we have. Over here we are coming inwards, so we will check that whatever the next cell is that we haven't checked, whether its height is greater than whatever the height we currently are at. So in this case, this is 3, this is 6, which means that okay, from this cell we can come to this cell, and over here we know that we are coming to this cell from this particular cell that is already able to reach to Pacific Ocean. So over here we can directly mark this one as true, and we won't have to do lot of calculation over here, because we already know that this cell is true and we are reaching to this cell via this cell, and this would be a very good solution. And this is how we can actually fill out this entire matrix or like all the remaining portion in big O of m cross n times in just single traversal, because we are not, for any particular cell, we are not going to check the whole thing. We are only going to check the cell that is exactly adjacent to it. So suppose we are at this particular cell and we know that this cell can reach to Pacific Ocean. We have already set this value as true. Okay, now we do calculations like this, and suppose before we come over here from this route, we have already calculated this and we know that this is already true, that this can already reach Pacific Ocean, and we are at this position and we are checking this again. So first we will already find that whether the value for this particular element has been calculated already or not. If it has been calculated, we don't need to do repetitive work and we can just simply skip over it. That way we can also make some runtime adjustments that would be more efficient on our case. Okay, now we need to find a way to somehow create the matrix that stores the information of all the cells that can reach to Pacific Ocean and also to Atlantic Ocean. In order to do that, at first I thought that we are going to use dynamic programming over here, and the reason I thought is because first of all we are defining a set of all the cases that can reach to Pacific Ocean. So this becomes our base case. Once we have our base case defined, we are essentially going in all the directions to see that if we can reach to next cells, and suppose in this case we are able to reach to this cell from over here due to the height difference, so we will mark this as true, and again from over here we will again do the same thing, and we will, so basically at any point we are using whatever the calculation we have calculated before to generate the next results. So that's a very clear indication that we need to use dynamic programming over here. But it turns out that I was not able to solve it efficiently. I was still missing out in a lot of test cases. So apparently dynamic programming is not the way to go, but I still urge that if anyone can solve it using dynamic programming, I would be more than happy to understand your approach. So second thing I tried to do is okay, in order to solve this we need to iterate over the entire matrix, and in order to iterate over the entire 2D matrix, we have basically two methods. We can use either breadth first search or we can use depth first search to iterate over all of the elements and do some calculation. Now I'm new to graph theory and I need to first of all perfect myself on depth first search before I move towards solving the problems using breadth first search. So I chose the approach of taking depth first search, but it can also be solved using breadth first search without any issues. And we know that in order for us to complete this program using depth first search, we need to use recursion over here, and of course we can use recursion because notice that at every single position, so over here first of all we define that this can reach to Pacific Ocean. Now we move on all the directions and over here we find the height difference. So again we know that this can reach to Pacific Ocean because this can reach to this cell, so we mark this as true, and then again we repeat the same process that we have just did, and again we would mark this as true, and again we would repeat the same process. So essentially we are doing the same sort of work but for different inputs, and that's a very clear indication that we need to use depth first search using recursion. And let's move on towards coding now. First of all, we are going to check the condition that if the given input is actually an empty matrix, then we just need to return null. Okay, if that's not the case, let's create two parameters to store the value of row and column. Now we'll create two Boolean matrix to see to store the value of cells that can reach to Pacific and Atlantic Ocean, and we are going to name that Pacific reachable and Atlantic reachable. And we are going to create both of them to the size of whatever the initial heights matrix we are given. Now we will run a for loop on for both the matrix to be filled out. In order to fill both the matrix, we are going to create a DFS method, and inside the DFS method we are going to provide the row and column location, and we are also going to provide Pacific and Atlantic matrix. So first we'll do it for Pacific matrix, and we are also going to provide the input heights that we are given. We are again going to call the same function for the Atlantic. We'll iterate using column as well. Now before we calculate the result, first let's create the method. Now inside the DFS method, we will have to iterate over, for any particular cell we will have to iterate over all 4 of its adjacent cells. So we'll just create a 2D array called directions, and we are going to use it to iterate over all the adjacent or neighboring cells. So we are at this DFS location, which means that we already know that this row and this column pair is already able to reach to subsequent whatever reachable matrix that we are trying to calculate. So which means that we will set that value as true. Now we will start iterating over the neighbors of whatever the current cell we are at, and we are going to create the new row and new column. Now we will have to check that if this new row and new column, are they out of bounds or not. If that's the case, we just ignore that and we continue. We also check that if we have if the new row and column cell if we have that value calculated before, we can also just ignore that case. Okay, if both the cases are not true, we will check that if the height difference of the previous cell and new cell is in our favor or not, which means if the heights for the new row and new column if that is greater than or equal to whatever the previous height was. If that is true, we will need to call the DFS function again with the new row and new column. And this would be our logic for this DFS method, because we are eliminating all the cases and we are also calling the recursive function based on the height difference. So after these 4 entries run, we should have both of our Pacific reachable and Atlantic reachable matrices filled out, and now it's just a matter of finding the common elements between them. So first of all, let's create a list of lists to store our result, and we'll just name it as result. Just going to iterate over the entire array row and column wise, and we are only going to check that if both the values are true in both the Atlantic and Pacific Ocean cells. So if both are true, we can add it to our list. So after this loop runs, we simply need to return whatever the result we found, and that should be our solution. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code. Okay, our solution also works. It is accepted by LeetCode, but the thing is it's not the most efficient solution. So let's see that if we can do some modifications. And one modification I can think of is rather than calling this DFS system right here and checking this condition all the time, what if we revert the condition, and if this condition is satisfied, we can just return it, and we can just continue before. So that's why loop breaks more times before. And if all of these conditions are not true, then only we will call our DFS function. Let's try to run the code. Okay, the code is working. Let's try to submit the code. Okay, we see some improvement in our code, and now it's a little bit faster than what our previous result was. So I'll be posting this code in the solution. You can check it out from there, from the comments, and let me know if how do you like the video. Thank you. So the LeetCode problem we are going to solve now is called surrounded regions. We can see that this one is a LeetCode medium problem and also very well like problem. Now the statement is quite straightforward, that we are given an m cross n matrix named board that contains bunch of different x's and bunch of different zeros. Now we need to capture all the regions that are four directionally surrounded by x. And if a region is captured, then we need to flip all the zeros into that particular region into the axis that is a surrounded region. So let's try to understand what they are trying to ask. We are given in this example an m cross n board where we can see that there are bunch of different x values and bunch of different zero values. Now in this case, what is the definition of any particular zero region to be surrounded? A region is surrounded if in all four directions it is connected by some sort of x in each one of them. If that is the case, we can determine that this particular region is surrounded. Now notice one important thing. We are not concerned with its immediate neighbor, but even if the neighbor of the neighbor is still a value x, then we can determine that that particular value is still surrounded by x's. So the moment we identify a surrounded region, all we need to do is convert all the zeros into x's, which means we can see that this node is surrounded by 4 x's in these four directions. Same way with this particular zero, it is surrounded by these 4 x's, and same way for this particular zero, it is surrounded by these 4 x's. So logically, all of these would be converted into the x's, which we can see over here. But for this particular region, it is only surrounded by x in 3 different directions, not 4. So we are not going to flip this 0 into x. We are going to leave it as it is. And then we need to return this state of the m cross n grid as part of the answer. So let's try to see that what is the simplest logic we can use to solve this problem. Now, let me give you one example of bunch of different zero potential values in all of these different grids. Let's say for this particular grid, if we have any single value 0, then that value has to be not surrounded region. Why? Because currently this particular value is located over here. Even if in all the other directions we have access, then also we would never be able to get a 4 directional pattern where this region becomes a surrounded region. So in the answer, we are always going to have a scenario where this 0 is going to remain 0. Same way for this 3 by 3 grid, let's say that if we have any particular 0 present over here, and let's say that all the other values are currently x's, then we can very easily determine that this 0 is actually surrounded by x's in all 4 directions. So in the answer, when we try to create, basically this 0 has to be flipped into x. That is true. But let's say instead of doing that, instead of this being 0 in this middle portion, let's say if we have 0 located at any of these edges, any of these, okay? I'm not saying all of them are zeros. Let's say any one of this is a 0, and let's say that all the other values are x's. So I'm currently marking these by a bunch of different x's. This region would never be surrounded. That's a given fact. Why it would never be surrounded? Because there is always going to be 1 or 2 directions where it is located on the edge, which means there can never be an x planted over here. So if the node is in the middle, then it has the possibility of being a surrounded region. But if we identify 0 at any particular edge, then that 0 is always going to be a not surrounded region. So it does not needs to be changed. That is what I'm trying to explain. Now let's try to see one more example in this case. Let's say if we have any particular these 4 zeros placed like this, and all the other values are x's. In this case, all of these zeros has to be converted into the x's, because all of this becomes a surrounded region. But for some example, if we have any particular 0 located over here, we already established that this does not needs to be changed. That is number one thing. Second thing is that not only this does not needs to be changed. Let's say that if there are any particular other zeros connected with this value, then also they are also going to be not surrounded regions. Once again, I repeat, if there are any particular zeros that are connected with this edge, then we can determine that this is also going to be not a surrounded region, and we are going to exploit this property to its fullest. Because remember, in this case particular, this 0 is actually always going to have one more 0 located over here, which means it can never be 4 directionally challenged by another 0. And this is what we are going to use to solve this problem. What we are simply going to do is that we are going to treat this as a graph problem. On not only a graph problem, we are also going to treat it as a graph traversal problem, where we need to do the depth first search. At any given moment we identify a value that is currently 0. The thing is, we are not just going to blindly start looking for zeros in all of these particular grids. That it makes no sense. If there is any particular 0 in the middle, there it might be possible that there might be excess in all 4 directions that could prevent it from becoming a not surrounded region. What we are going to do is we will try to only traverse into the edges of this particular matrix, and for each of the edges we will try to find that if there exists any particular 0, then we are going to start doing the DFS, and all the values that we identified through this iteration, we are just going to mark those numbers that they are always going to be 4 directionally not surrounded regions, and all the other regions or all the other values we can simply mark them by X. So let's try to understand this with an example that I'm trying to show you. Let's say that in this case we are currently given that these two nodes are currently zeros, and let's say that this is connected with this 0, and let's say that this one is not connected with anyone else, and then we have this 0 connected like this, and all the other values are currently X values. So logically the algorithm I'm proposing is that we start iterating over this m cross n grid in first of all the edges. So let's say that these 4 are the edges, and then we once again identify this edge and this edge, and then this edge and this edge. So we found a one edge that contains a value 0. The moment we identify one edge that contains the value 0, first of all we are going to mark this one as a special 0. So let's say that I'm keeping track of all the zeros that I have been able to identify so far, and let's say that this one is a special character that contains a 0 at the edge. Then we are going to do the DFS operation in all 4 directions to find all the connected zeros. But we can see that this one does not have any connected zeros. So we are just going to say that this is the only 0 we find, and then continue with our iteration. Once again we are at this position, this is also X. Once again we identified one more 0. So the moment we identify one more 0, we are going to mark it as a special character, and then we are going to start doing the DFS operation in all 4 directions. This one is an X, so we don't do anything. This one is an X, so we don't do anything. But this one is not an X, so this one is also a 0, and a 0 that has been found by reaching a 0 that was present in the edge. So once again we are also going to mark this as a special character, and then now from now on we cannot move ahead anywhere forward, so we cannot do anything. On top of it, for our DFS operation we will have to keep track of all the visited nodes, so we are also going to mark all the visited nodes as well. So it's just simply for our convenience, and that's it. So once again we don't find any more access, so then we simply say that we iterated all the edges. We did the DFS on whenever we found a 0 at the edge, and we marked those nodes, and apart from these nodes everything else should be converted into the x's, which means this node has to be converted into an x, and that's it. This is the state of m cross n that we need to return of all the zeros that are not surrounded, and all the surrounded regions are being converted into the x's. So that's it. This is the whole solution. If we try to understand the time and space complexity, in this case time complexity is going to be big O of m cross n, because we will have to iterate over every single nodes, and this is an example of adjacency matrix kind of representation for the graph. Space complexity, well, this is debatable. If you have to create a new snapshot, then you might have to use m cross n space. If you can modify this current existing node just by changing this character from something else from 0, maybe something like a hash or something, then also we can use the same pattern or same logic. So it's up to you how you want to approach that, or how your interviewer wants to do that. It can be a common space complexity, or if you are not allowed to change the input, then it is going to be big O of n cross n space complexity. So now let's try to see the coding solution for this one. So the coding solution is quite straightforward. We need to solve the given board, and first we are going to check for the edge case, that if the given board is equal to null, we can simply return. If that is not the case, we are going to define our m and our n. Then we are going to start iterating over the boundary and start marking all the zeros that we find on the boundary as like a temporary character or a temporary variable. So let's say that we run two loops. We have this if condition that if the given node is equal to 0 or m cross m minus 1 and j is equal to 0 or n minus 1, which means we are checking for the edge nodes. On top of it, we are also checking that if the given board position marks the value as 0. If that is the case, then we are going to call our DFS method. In the DFS method, we are checking that all the surrounded regions that we need to find. So this is our DFS method, where we are first of all checking that if the given node is equal to null, or we exhausted all the possibilities, we can simply return. If that is not the case, we are going to mark that particular value as a temporary character t, stating that this has been visited, and we are going to run the DFS operation in all four directions repetitively, which means we are only going to be left with temporary values that are currently visited by us after this DFS operation, that are connected with the zeros that are located at the edge. Then once that is done, we simply need to check and capture all the surrounded regions. So for that, we can simply iterate over the given input array and check that if the given input board position is equal to 0, which means it is not t, then we are going to simply mark it as x. If that is not the case, and if that value is t, which means it is not a surrounded region, so we are going to mark it as 0. And that's it. This is the whole solution. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code is exceptionally faster compared to all the other solutions, which is great to see. And once again, you can find the solution on my GitHub repository. Link is in the description. Thank you.
Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do course schedule lead code problem, and this is one of the most versatile problem that has been asked at bunch of different companies, like huge number of companies. We can see the companies like Amazon, Microsoft, Facebook, Google, TikTok, Snapchat, Robinhood, Twilio, Uber, eBay, Tesla. All the companies have asked this question, and this question is very practical, real life application. So that's why a lot of companies like to ask this question. So this is a LeetCode medium problem, and we are given a number of courses, and we are also given an array of prerequisites, where any single entity in array is defined like this, where we are given two values, suppose a and b, separated by a comma, which means that we must complete course b first in order for us to complete course a. So suppose we are given an entity in the prerequisites like this 1 and 0, which indicates that this course 1 actually has a prerequisite called course 0. So we can define it like this, that course 1 has a prerequisite on course 0, and in terms of the practical manners, we first complete this course 0 in order for us to complete this course 1. And based on the information given, we need to check that whether we can finish all the courses or not. And if we can finish all the courses, depending on whatever the prerequisites we are given, we need to return true, otherwise we need to return false. Okay, now that we understand the problem statement, let's take a custom example to understand the problem. Suppose we are given the list of prerequisites like this, and we are given the number of courses as 4, which means that we need to complete the 0, 1, 2 and 3. These 4 courses we need to complete, and this is the list of prerequisites we are given. Now we can consider this as actually graph problem. We can consider these as graph nodes, and the prerequisite information, we can treat them as graph edges. So over here we can say, let's plot it on a graph and let's see that how it would look. So over here, 1 has a dependence on 0, so I mentioned this. 0 has a dependence on 3, so let's also mention this. And 2 has a dependence on 0, so
2 has a dependence on 0. Okay, so this is how we can plot this on a graph, and we need to see that whether we can complete all of these forces or 4 courses or not. So the most intuitive solution is to check from the beginning. We check at this course number 0, that can this course number 0 be completed or not. Now in order for us to complete this course number 0, we see that this course 0 actually has a edge pointing towards course number 3, which means that course 3 is a prerequisite for course 0. So we need to complete this course 3 before we can complete course 0. Now we are at this course 3 again. We check the same thing, that whether we can complete the course 3 or not. Now course 3 does not have any prerequisite, which means it can be completed on its own. So we say that okay, course 3 can be completed. Now again we backtrack to 0. At 0 we check that does 0 have any other prerequisites that we need to take care of. No, 0 only has one prerequisite on course 3 which we can complete, which means that we are able to complete course 0 as well. So we can mark this and the square box indicate that we are able to complete that course. So we are good. So we already know that 0 can be completed, 3 can be completed. Now we check for this course number 1. So at course number 1, we check that what are the prerequisites for course number 1. Well, course number 1 has a prerequisite on course number 0. So since we already know that course 0 can be completed, which means we can also conclude that course 1 can also be completed, which we can mention over here. And we can check for this course number 2. So course number 2 also has a prerequisite on course 0, which is already done, which means we are able to complete course number 2 as well. So in this case, for all the 4 courses, we are actually able to complete them, and we can return true in this case, that yes, based on the given number of courses and prerequisites, we are able to complete all the courses. Now we need to check that what could be the scenario if we cannot complete the course. So suppose we are given an additional edge like this in the same example. Suppose we are given this additional edge. Now let's see that how the dynamic would change. Let me clean this up a bit. Okay, now we have this additional edge 3, 2, which means that in order for us to complete this course number 3, we would need to complete course number 2 as well. Now let's see that can we complete. So initially we would check that can we complete this course 0. So in order for us to complete course 0, we would need to complete course 3. Okay. Now in order for us to complete course 3, we would need to complete course 2. Okay. And again, in order for us to complete this course 2, we would have to complete this course 0. So notice that we are constantly stuck inside a loop. It's the same scenario where you need experience to gain a job and you need a job to gain experience. It's somewhat similar kind of example, that we are stuck inside the loop, which means that no matter what happens, we are not able to complete any of these 3 courses without completing the other one, because there is an interdependence between each other. And essentially in this case, we would have to return false, that we cannot complete all the courses. But the thing is, why did we had to return this false? Well, the reason is quite simple. Basically, in terms of graph manner, if we speak, what was the difference from this graph compared to this previous graph? Only this edge. And when we added this edge, what essentially we did was we introduced a loop inside our graph amongst these 3 values, 0, 2 and 3. So we can conclude one thing, that at any given moment, if we've identified that there exists a loop inside our graph, we would be able to immediately return false. If there does not exist a loop and we are able to, from every single element, we are able to complete all these prerequisites, in that scenario, we need to return true. So now we have these 2 information. Let's see that how can we use them and how can we solve this. So suppose we are given an example like this, and these are all the prerequisites that we are given, and we need to complete the total 6 number of courses in order for us to conclude that this graph can be scheduled or not. So essentially we are going to apply the same logic. We are going to first of all take these inputs, we are going to convert them in a graph like this. Inside the graph, for every single course, we are going to see that whether we can justify these prerequisites or not, and at any moment, if we identify that there exists a loop, we will immediately terminate and return false. If there does not exist a loop, we would keep going, and eventually we would return true. So that is the idea. And in order for us to achieve that, first of all, what we are going to need is, we are going to need some sort of graph data structure, because initially the only two values we are given is number of courses and the set of prerequisites. So first of all, we would create a data structure like hash map, and inside of our hash map we are going to store two values. We are going to store, as a key we are going to store the number of courses, and as a value we are going to store the number of prerequisites that every single course has. So initially we would have, so this is the number of courses and these are the prerequisites that we have. And we would try to see that can we complete all the courses or not. So first of all, we are at this course 0. So in order for us to complete this course 0, we need to see that what are the prerequisites for course 0. So for course 0, the prerequisite says course 2. Now for this course 2, what is the prerequisite? The prerequisite is actually course 3. Okay, and now for this course 3, the prerequisite is actually course 4. So here, and for this particular course 4, the prerequisite is actually course 5. So here, now we are at this course 5, we check that can we complete this course 5, and yes, we are able to complete the course 5 because there exists an empty list. So which means we can conclude that course 5 can be completed over here because there is an empty list. So again we backtrack, we go back to course 4. At this course 4, we know that course 5 can be completed. Since course 5 can be completed, we can also have an empty list over here because it defines that at any moment, if we are at this course 4, that course 4 can always be completed because its prerequisites are already met. So we can have an empty list over here. Now again we go back. If we go back, we are at this course 3. So in order for us to complete this course 3, we would need to set up an empty list over here because course 4 can be completed. That is done. Now again we come back to this course 2. At this course 2, again we will create an empty list, and now we are at this course 0. So at this course 0, we only have dependence on course number 2, so we can also have an empty list over here, basically defining that course 0 can be completed. Okay, so that is one observation that has been done well. Now, and see that we were only trying to calculate that can we complete this course 4, but we already concluded that we can complete all these courses as well, and we have already established them inside our hash map. So at any moment, we only need to identify the remaining courses and not all of these courses that we have solved already, which means we are efficiently improving our solution. Second, we come at course 1. Now this course 1 actually has 3 dependencies, course 2, course 4 and course 5. So let's take care of each of them one by one. First of all, we will check that from course 1 can we complete course 2. So we check for this course 2 and we check that these prerequisites are already met because there exists an empty list, which means that we can eliminate course 2 from over here from the list of prerequisites because we know it can be completed. Again, we check the same thing for this course 4. Over here, this course 4, we again have the empty list, so we can also eliminate the course 4 over here as well. And again, we can repeat the same process for this course 5, that course 5 can also be completed because there exists an empty list, which means even at this position course 1, we can create an empty list over here. And now if we look at all the courses, the only prerequisites we have are just empty lists. And once we achieve that, basically we can conclude that we have already reached our solution and we can return true in this case. So this solution works perfectly fine. But the thing is, we missed the key point over here. Like, because this was a true scenario, we did not identify any issues. But the thing is, if there was a loop, we were not actually checking that whether we are encountering any loop or not. So let's see that if we want to encounter any loop at any iteration, what would be the additional steps we need to take. So let's modify our example a bit. Suppose we have an additional prerequisite like this 5-3, that in order for us to complete this course 5, we will need to complete course 3. So we will have an edge like this, and let's modify our prerequisites table. Okay, now in this example, we know that there exists a loop between this 3, 4 and 5. So we need to take care of it, and in order to take care of it, I'm suggesting that we create an additional hash set at the beginning of checking for any single course. So we create a hash set, and in our head we just name it as visited or something. And over here we will keep track at any location are we repeating the same element. So let me show you what I mean by that. So initially suppose that we are at this course 0 and then we start our program. So we want to check that whether we can complete course 0 or not. So first of all we will check that whether we have already visited this course 0 in this current iteration. So we check in this visited node that have we visited course 0, and because it's a hash set, it's a constant time operation, so we are not adding any additional strain on the time complexity. So we haven't visited this node 0. We would add an entry over here first. Now we will check over here that what are the prerequisites for this course 0. So the prerequisite is course 2. So again we would check our visited node first. So course 2 is not part of it, so we would add an entry over here, and again we would continue over here. So now we need to check this course 3. Again we would add it entry to the visited node. We check over here, we need to check course 4 we haven't visited, so we would add an entry over here. Then we would check the force prerequisite 5 we haven't visited, so which means we would add an entry over here. And now at this 5 we would check the prerequisite for 5. So for the prerequisite for 5 is actually 3, so we are again at this position 3. So first of all we will check that whether we have visited this 3 or not, and this time we would know that yes, we have already visited this node 3, which means that we are in a loop. So this is what this hash set confirms, and the moment we find out, we can immediately return false over here. We don't even need to check any additional items in this given graph, and we would be able to terminate our case immediately, which means, and in case if this edge was not existent, this entry for this value number 5, we wouldn't have to check anything, and we would have been able to complete all our code, and we would have been able to return true, but which is not the case this time, because there exists an additional prerequisite as specified over here. So this would be our final solution. And now let's calculate the time and space complexity for this one. So for time complexity, we can actually complete this whole thing in big O of v plus e time, because at any moment the maximum traversal we will have to do is from one node to all the single nodes, and throughout all the single edges. So this would be the time complexity. And space complexity, because we are creating an additional data structure like this hash map and also this hash set, but the thing is hash set is going to be smaller, so we are only concerned with this hash map. For general time complexity, it would be space complexity, it would be big O of v plus e as well. Okay, first of all we will create a hash map, and we are going to store integer and list inside it. We will name it course graph. Okay, now we will have to build our graph. So essentially we are going to iterate over every single prerequisite in the given prerequisites, and first of all we will check that whether this prerequisite is already added in our graph or not. So if it is added already, we only need to append the new prerequisite, and if it does not exist, we will need to create a new one. We'll have to create a new entry in our course graph. So we will create a new list and add the list, and then we will add the entry of the course and the list to our graph. Okay, so after this loop ends, we should have our graph structure ready. So now we will create a hash set that will take care of integer values, and we'll name it visited. And now we will have to run a loop for all the courses that we are given. And now we will have to create a method to check that whether there exists a cycle inside the loop or not. And let's name our method that course schedule, which indicates that whether we can schedule a course or not. In this course schedule method, we are going to provide the current course,
the visited node, and the graph that we had created. And if this responds back to false at any given moment, we would know that we cannot create the course schedule, so we will return false immediately. And if this loop ends and we don't return false, which means that everything was successful and we can return true. Okay, now we will have to create this course schedule method. So let's create a boolean method. Now let's test our terminating cases. So if our set contains the current course, which means that we have detected a cycle, so we can terminate immediately, so we can return false. Also we check that if for the current course if we already have an entry in the graph where it has an empty array list, we can return true. If that is not the case, we will have to iterate over all the prerequisites for any particular course. So first of all, we will add the current course that we are iterating over in our visited hash set. Then we will iterate over every single prerequisite for that particular course. We would call our recursive function. So and we will provide the current prerequisite we are at. We will provide the visited hash set, and we will provide the graph. And if at any point this returns false, we can return false immediately. However, if this loop executes, we know that for that particular course we are actually able to complete the course, and we can schedule it. So first of all, we will remove it from the visited node, and then now since we know that this particular course can be completed, we would update the entry for that course in our course graph. So we would set the prerequisite to null, which means that in future at any point if we identified this particular course, we know that we are able to complete it and we can just move forward quickly. And at the end we can simply return true in this case. So I guess this would be our course schedule function where the main logic happens. And let's try to run the code. Okay, seems like our code is working. Let's try to submit the code. Okay, our solution works, and it works pretty efficiently. So I would be putting this solution in the comments. You can check it out from there. And this was a really long video. It took me a lot of time to make it. So I hope you like it, and let me know in the comments on what are your thoughts about this problem. See you next time.
Hello friends, I'm a cloud solutions architect at Microsoft, and my aim is to empower every single person to become better at technical interviews. Keeping with that goal in mind, today we are going to solve a very important LeetCode problem. So let's get started with the problem. So today we are going to do course schedule 2 LeetCode problem, and if we see some of the popular companies who have already asked this question, there are companies like Amazon, Google, Microsoft, TikTok, Apple, Plantier, ByteDance, Roblox, Uber, Facebook, Robinhood, Snapchat, Bloomberg, DoorDash, Lyft, and Goldman Sachs. So this has been a very popular question at many different companies. I'm going to pay my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and also very well liked problem on LeetCode. In this case, we are given two items. First item is number of courses. Now the number of courses, it says that suppose we are given number of courses to be 3, which means that we are given the courses 0, 1 and 2. Suppose we are given the number of courses to be 5. In this case, the courses are 0, 1, 2, 3 and 4. So this is what the number of courses defined. Second item we are given, which is more important, is the array of prerequisites. Now, what does an array of prerequisites define? Well, there can be a structure that looks like this, A, B. What this means is that course B is a prerequisite for course A. We all know that we need to complete like the prerequisite course in order to go and do the more advanced level courses. So in this case, if we complete course B, then we are eligible to complete course A. But say for example, for some reason we are not able to complete course B, we are guaranteed that we would never be able to take part in or be eligible to complete course A. Now, after having these two items, number of courses and prerequisites, basically what we need to do is we need to return an ordering of courses such that we are able to finish all the courses. And what does finishing all the courses means? That we are abiding by the list set of or the all the prerequisites that we are given amongst all the courses. And definitely there could be many different answers to that. We can complete the courses in many different ways, so we need to return any of the valid answer. And for some reason, if we are not able to complete all the courses, we need to return an empty array. So let's try to understand this with few examples. So in the first example, we are only dealing with two courses. So the two courses are going to be 0 and 1. Now for these two courses, we are only given one prerequisite, and this prerequisite says that course 0 has to be done in order to be eligible to complete course 1. So if we complete the courses in the ordering of 0 and 1, then this is going to be a legitimate answer, where we complete the course 0 because it has no prerequisites, and since we have already completed course 0, we are eligible to complete course 1, and this is going to be a valid answer, so we can return this as the answer. If we take the second example, this is a little bit more complicated. Now we are dealing with 4 courses, which means courses are 0, 1, 2 and 3. Now in this case, if we see, there are a bunch of different prerequisites. So let's go every single one of them and try to find some answer. So first one, it says that course 0 has to be done before we can do course 1. Okay, that is good. Second one says that course 1 needs to be completed before we are eligible to do course 2. So we have already completed course 1 over here. So let's try to do course 2 after that. Then it says that course 2 has to be done before we are eligible to do course 3. So over here we are already done with course 2. So let's complete course 3 after that. So this is one of the valid orderings. And in this case, if we return 0, 1, 2 and 3 as the answer, this is going to be a perfectly valid answer. And in this manner, we are keeping track of all the prerequisites and we are also completing all the courses. Let's take one final example. So if we see in this final example, this is a little bit different example. So over here we are given 3 courses. So courses are going to be 0, 1 and 2. Now we are given some prerequisites. So let's try to go through each one of them. So first one is 0 to 1. Okay, we need to complete course 0 in order to complete course 1. That's good. Now second one, it says that we need to complete course 1 in order to complete course 2. So 1 we have completed over here. Let's create it for 2. But now this prerequisites, it's a little bit tricky. And the tricky part is that we need to complete course 2 in order to complete course 0. Which is the tricky part, because now if we see, there is no way for us to complete like all 3 courses, because every single time we are going to be bounded by some other course. Because definitely in order to complete course 1 we need to complete course 0, in order to complete course 0 we need to complete course 2, in order to complete course 2 we need to again complete course 1, but we cannot complete course 1 because 0 hasn't been done. So this is going to be keep running in the round and round, and this is a huge problem. So in this case, we are simply going to return an empty array because we cannot find an ordering that satisfy all the properties. So based on my drawings and all the logic I'm trying to show you, it becomes pretty trivial that how we are going to solve this problem. The way we are going to solve this problem is using graph theory. And for the graph, we need 2 items. We need nodes and we need edges. So as the nodes, we are actually going to use the number of courses, that all the courses are going to represent a node in itself. And for the edges, we are going to take all the values that are present inside the prerequisite table, and based on that we are actually going to create an edge, and that is going to give us very interesting results. Now in this case, say for an example, just consider this example and let's try to draw a graph in this case. So first one, okay, we are given 4 courses, so we are going to draw 4 nodes. So first prerequisite is that we need to complete course 0 in order to complete course 1, which means 0 is actually a prerequisite for course 1. So we can have an edge between 0 and 1, where 0 is a prerequisite and 1 is the node that needs the prerequisite of 0. So notice in this case I'm only drawing one directional edge. Why? Because for 1, 0 is a prerequisite, so that's why there is an edge between 0 to 1. But the thing is, for 0 there is no edge coming back from 1, because so far we haven't find that there is a prerequisite in this case. So because it is not the case, we are simply going to keep progressing. Now next one is that we need to complete course 2 in order to complete course 1, right? So basically from 1 to 2 there is also going to be an edge, because course 1 is a prerequisite of course 2, and course 1 has to be done before we can proceed to course 2. So that is why there is an edge from 2 to 1 to 2. Same way, we must do course 2 before we can proceed to course 3. So we must do course 2 in order to proceed to course 3, and this is also a prerequisite. And this is a graph that is being made based on the number of courses and the array of prerequisites that we are given. Now our aim is to find any legitimate offering. So in order to find any legitimate offering, the logic is going to be quite simple. What we are going to do is we are going to pick any single node and we are going to do a depth first search. Now in the depth first search, we will have to keep track of like 2-3 items. First thing we will have to keep track of is that there are no cycles. If we find cycle, basically we have entered a scenario where we are not able to complete all the prerequisites. Say for example, in this case, if we are given an additional node that looks like this, or sorry, an additional edge that looks like this. So in this case, we have actually detected a cycle, and because we have detected a cycle, there is no way for us to complete all the courses. So definitely in this case, we will have to return an empty array. But lucky for us, in this case, we are not given a prerequisite that looks like this, right? So we found no cycles. Second thing we need to do is we can pick any single node, and from that node, if we start iterating over all of its neighbors in the DFS manner, and then keep a track of all the elements that we have visited, by doing that we won't be able to find any cycles, and also we will try to order them in a manner that we match all the dependencies, and in the end we simply need to return the ordering. So this is going to be a perfect logic to solve this problem, that we are taking consideration of everything. Now let's see that we know the core logic, that how we are going to use it. Let's see how we are going to implement it. So in this case, we have total 7 courses that we need to take care of. And for all of these 7 courses, I also have a prerequisite array. Now, based on these two things, we know that for any single graph problem, we need a way to represent the entire problem in a graph manner. So how we can do it is we have two ways. We have adjacency list and adjacency matrix, right? So in this case, I think we are good with going with adjacency list rather than adjacency matrix, because the graph is not going to be too sparse, and so let's try to stick with adjacency list. Now based on this given array, we would be able to create our adjacency list. Now how we are going to create our adjacency list? Well, basically for adjacency list, we are going to create a hash map. Now inside this hash map, we will have to take care of two values. First one is like the key, and second one is its value. So as a key, we are going to take all the courses that are present, and as the value, we are going to take that which courses, like for that particular node, for whom it is the prerequisite. Again, I'm repeating myself. So as the node, we are going to take all the courses. So basically the nodes are going to be 0, 1, 2, 3, 4, 5, 6, 7 over here. And as its value, we are going to see that for what are all the courses it is a prerequisite for. So let's try to draw our graph and also fill up our prerequisite table. Okay, so based on the given prerequisites, we have been able to draw our graph. Now, if we see on the graph, graph is only for our explanation. Basically, all we will have to do is we will have to create our prerequisite adjacency list that I mentioned. Now in the hash map, these are all the nodes or the number of courses as mentioned. And now let's try to keep on mentioning their prerequisites. So first we will see that for what are the courses, 0 is a prerequisite. So from the graph, we can actually take a look at this prerequisite array as well. But the thing is, I feel it would be better if we just do it from the graph. It would be easier to visualize. So in this case, basically course 1 and course 2, these are the two neighbors, or these are the two edges that derive from course 0, which means unless completing course 0, we cannot complete course 2 or course 1, because for both the courses 0 is a prerequisite. Same goes, okay, let's see for course 1. Course 1 is actually a prerequisite for course number 6. Okay, that's cool. For course 2, okay, course 2 is a prerequisite for course number 4. And 6 actually has no prerequisites. Okay, now we have done half of the work. We have created our graph. Now the question is how we are going to traverse the graph, how we are going to make sure that we are finding cycles, and how we are going to keep track of all the answers, that what should be the correct ordering. So these are the three tasks we will have to do. So the traversing part is pretty easy to solve. We are simply going to use the DFS and we will keep on iterating. The question is how we are going to detect cycles, whether they exist or not. In order to do it, basically from any single node, if we are going to do a DFS, we will have to keep track of that at any given position. We are not coming back to that particular node that from where we started. So we will have to find a way to keep track of all the visited nodes. So one of the best way to keep track of visited node is using hash set. So we are going to use couple of hash sets. There is also another trick where we can give the nodes some numbers and or some colors where we can treat them as such that whether they have been visited or not. But for explanation purposes, let's just keep track of hash set. When we go to the coding, we are going to use it differently. Now we also need to keep track of the ordering. The idea we are going to use over here is that we are actually going to use a stack. Initially the stack is going to be empty, and from whatever the node we started visiting, we will keep on visiting until we reach to a point where it does not have any prerequisites or all the prerequisites has been met. Once we get to that point, we would add that course into our stack. Eventually our stack is going to be full. And remember, the idea of a stack is that in the stack we keep on adding all the values. When we pop off all the values in the reverse manner, then we add it. So basically we are adding the first value inside that contains basically all the prerequisites, and then we will keep on adding values on top of it. So the top value inside our stack is going to be a value that contains no prerequisites, and then we will keep on popping one value at a time, and in the end we should be able to get our answer. So after this long explanation, let's see all of these things in action. Okay, so now we have our structure ready. I have created an adjacency list over here. Now for this adjacency list, first of all we are going to do DFS. So I'm going to keep track of that what element we are DFSing over. We are, for any single DFS that we are doing, we will also have to keep track of the current visited nodes that we are going through, because during the DFS we do not want to find any cycles. So if any element appears in the currently visited elements during the same DFS, we would know that we have encountered a cycle, right? Suppose we do not encounter a cycle and we reach to an element, say for example like 6, that does not have any prerequisites, then we can simply conclude that that node is a good node to be added to the stack. So we will simply add it to the stack. Once adding to the stack, we will also add it to the node of visited nodes. What this would do is, this would allow us not to do redundant work or not to do duplicate work. So let's see the whole calculation in action. Okay, so first we are going to start DFSing over the first element. So we are going to start with element number 0. If we start with element number 0, what are the neighbors or what are the values for element number 0? Okay, so first value is value number 1, right? So currently we are visiting, okay, initially we started our visit with element number 0, then first element we are visiting is currently 1. Now we are going DFS, which means we are going in depth. So even for node number 1 we are going in depth. So node number 1 has is a prerequisite for course number 6. So which means if we want to get to course number 6, we will have to go through 1. So now we will go to course number 6. So currently we are visiting course number 6. Now course number 6 does not have any is not prerequisite for any of the courses, which means this is wonderful. So now what we can do is we can conclude course number 6 to be done. So we will take the course number 6 value from here and we can actually add it to our stack. So if we add the value number 6 to our stack, okay, now we have added a value number 6, which means course number 6 we have already put the ordering for that. If we put the ordering for that, which means we have already visited that course. So we are going to add an entry in our visited hash set. Now let's go back. Now if we go back, okay, we still have one more element 1 that we haven't processed, right? So if we check for element 1, does it has any other prerequisites, or is it a prerequisite for anything else apart from 6? No. So which means this is done. So for 1 we do not have any more courses where 1 could be a prerequisite, which means 1 can also be added to stack. So we will add entry number 1 to the stack as well, and also at the same time we would define 1 has also been visited. Now we go back to course number 0. So for course number 0, currently we have taken care of this course number 1, but we haven't taken care of this course number 2. So we will keep on iterating. So currently now we would visit course number 2. For course number 2, do we have any ways to go to next course? Yes, we need to go to course 4. We will have to go through course 2. So we can go to course 4. Now for course number 4, is it a prerequisite for anything else? Yes, it is a prerequisite for course number 5. So in order to go to course number 5, we have to go through course number 4. Now for course number 5, okay, course number 5 can go to course number 6, but the thing is 6 has already been visited, so we can ignore this case. If we ignore this case, course number 5 is no longer prerequisite for any other courses, which means now course number 5 is actually ready to be added to our stack and also visited hash set. So let's do that. We will remove course number 5 from here. We will add that 5 has been visited, and we will add an entry 5 over here. Awesome. Now we have course number 4. So for course number 4, okay, apart from 5 it did not add anything else, so which means course number 4 is now also eligible to be added to the stack. So we will visit course number 4 and we will visit course number 4 to our stack. Now for course number 2, let's see if there are any more entries. No, there are no more entries. Awesome. So now we will put course number 2 over here as well. So 2 added and also 2 added, 2 removed from the current stack, and now we are back to the course number 0. For course number 0, okay, we already took care of course number 1. Now we also took care of course number 2, which means 0 is now also eligible to be added. So awesome. Let's do that. So we add 0 over here and we add 0 over here. That's great. Now if we go back, this has been jumbled up, so let me clean this up a bit. Now in this case, okay, now we took care of course number 0, right? Now for node number 1, we will check our visited hash set. So in the visited hash set, yes, we have already visited course number 1, so we don't need to do anything. Course number 2 has already been visited. Awesome. Course number 3 hasn't been visited. So now for our current DFS, we will start visiting course number 3. Okay, so for course number 3, it has many different prerequisites. So course number 3, okay, course number 3 is a prerequisite for course number 1. So currently we are visiting course number 3. Let's see, course number 1, okay, 1 has already been visited, so we do not need to visit this one. 4 has also been visited, we do not need to visit this one. 5 has been visited and 6 has been visited, which means all of the courses which could lead us to these courses have been visited, which means course number 3 is no longer prerequisite for any other courses. So it is a good candidate to be added to our stack and our visited hash set. So we can add it to our stack and we can also add it to our visited hash set, right? Awesome. Now if we see our stack is already full, so do we need to worry about adding these more courses or checking for them? No. But if we want, we can do it. It would only be constant time because all of them, they have already been visited, so we don't care. Now since we have our stack ready, let's try to pop out all the values sequentially. If we pop out all the values sequentially, this is going to lead us to our answer. Why? Because, okay, first we have to complete course number 3, then 0, then 2, 4, 5, 1 and 6. If we complete courses in this manner, we would be able to meet our prerequisite. So let's see that whether our answer that we received, is this a valid answer or not. Let's compare it with the graph that we created. Okay, so now we have both the values side by side. Let's see if we start iterating. So if we first complete course number 3, then we would be able to finish a lot of different courses. So we won't have any prerequisites for course number, all of them have some other prerequisites, but if we do course number 3, there is no harm, so that is good. If we do course number 0, that is also good, right? Now can we do course number 2? Yes, course number 2 only has prerequisite on 0, which we have already completed, so we can do course number 2. Can we do course number 4? Yes, course number 4 can also be done because it had prerequisites on course number 2 and also course number 3. Both of them have been done. Awesome. Now for course number 5, okay, 5 can also be done because it had prerequisites on course number 3 and course number 4. Both have been completed. course number 1. Course number 1 only had prerequisites on course 0 and course number 3, both have been completed, so we can do that. And also for course number 6, it had actually prerequisites on course number 1, 3 and 5. All 3 of them have been completed before. So this is a legitimate valid ordering that we can use. And this is a great way to solve this problem. See time and space complexity. In this case, the time complexity is actually going to be big O of V plus E, where V is the number of vertices and E is the number of edges. And if we see space complexity is also going to be big O of V plus E. And this is a great example. And also the way to find this ordering is also topological sort. So congratulations to you. You also learned a new algorithm. So since this video is already too long, the code solution for this problem, I'm just going to explain it and then paste this code in the comments so you can check it out from there. Okay. So first of all, we are actually doing things a little bit differently than what I explained. Basically, we are creating 3 different like white, gray and black values. So this is going to be assigned to every single node. White is going to represent that the node hasn't been visited or it hasn't been touched so far. Gray means that during the current DFS, this has already been visited. And black means the code that is already going down into the stack or that we have created, which means from where we can fetch it and use it for the answer. Now let's go to our main method first. First, we have this find order method where as an input we are given number of courses and we are also given prerequisites. Now first thing we need to do is that based on the prerequisite, we are actually going to create the adjacency list. This is what we are going to create as I explained in the explanation. Now after this adjacency list, we are going to assign every single value to the white color for the first time. Why white color? Because it hasn't been added to any list or it hasn't been visited. And then we are going to go over every single values of this adjacency list and call our DFS function. Now what does this DFS function is going to do? It is going to recursively call all of the values or all of the neighbors of that particular node until we reach to the end. Now let's see what happens inside the DFS function. We receive a node as an input. Now we have a boolean value is possible. That is going to check that whether we have been able to find any cycle or not. And how we are going to be able to find a cycle? By using this gray color. So if a node that is already assigned a gray color and somehow in the DFS we find it to be gray again, which means we came back to the same node which we have already traversed during our current DFS. So there is a cycle present. So this is a good way to detect that. And for that we just created a different method that if the given color is gray, we simply get the DFS method. We simply assign the values is possible to be false. Okay, now in this case, first we assign the value to gray for any particular node that we are visiting. Then we start visiting all of its neighbors. Now for every single neighbor, we are only visiting the node that the color where the color is white. If the color is black, we are going to ignore that. If the color is gray, we are going to assign the value is possible to false, which means that this is not possible to do it and we can simply return an empty array in that case. If not, basically recursively we are going to call our DFS function for every single neighbor, and for every single neighbor we are going to assign the value to gray, and we are going to keep on doing it until we reach to a point where it does not have any more neighbors left. So at that time we are going to put the node and assign it to color black, and also we are going to assign it to a topological order list that we have created. Recursively, if we keep on doing it, basically our topological order list is going to be basically our stack where we would have all the values filled up. And once that is done, from our main method, we will check that, okay, if this is possible, if that is true, which means if this is still possible, then we will simply iterate over all the number of courses, and we are going to create a new array called order. For this order, we are going to take all the values in the reverse from the topological order, and we are simply going to return the order list that we just created, and this is the whole solution. So I would be posting this in the comments, so I hope you understood it. And if we try to run the code, this runs perfectly fine. If we try to submit the code runs decently efficiently. And yeah, so let me know in the comments what you think about this.